Bom, como eu comentei, estou diretora da Anritsu Brasil, tive o prazer aí desse primeiro projeto de trazer algo bem relevante para a tecnologia, mas tenho aí meus 15 anos dentro da área de teste e medição, acompanhando aí até um pouquinho por esse histórico, universidades, indústria se desenvolverem e sociedade se desenvolver também, né? E demandas de centros de pesquisa, então trago um pouquinho desse histórico, né? Eu sou formada em engenharia, aí dá mais uma alegria para essa de estar nesse movimento tecnológico. A Cíntia, que está aqui com a gente, é representante da Anritsu, né? Doutora, como muitos de vocês já conhecem, até não vou... Está diretora de P&D dentro da Espectro, que é a empresa que ela toca. E aqui em Campinas, né? Cuidando aí de teste e medição, com experiência aí mais de 20 anos na área de RF. E... mais de 20 anos. Né? Mais de 30 conta mais de 20, né? Estamos aqui também com o Torrone, a presença do Torrone aí trabalhando na Anritsu, não precisa... O Torrone dispensa, né? Comentários de quanto tempo aí de experiência. E aí, falando um pouquinho do Arno, né? O Arno, que vai fazer essa apresentação aqui para a gente, ele é um engenheiro de aplicação da Anritsu. Eu vou usar um pouquinho de cola aqui, gente. Eu passei aí as últimas 3 semanas com ele, e é uma pessoa excepcional. Eu gostaria de fazer essa apresentação em inglês, né? Porque a gente vai fazer o switch agora para inglês, mas eu acho que o inglês não tem palavras para descrever tão bem, né? O profissional que a gente tem aqui, o professor Hugo também, a Cíntia, mas é uma conexão, uma oportunidade de conexão que a gente tem no Brasil, sem igual, de trocar experiências, né? E de facilitador. Alguns de vocês aqui tiveram a oportunidade, o quanto que a didática dele e a preocupação dele em compartilhar conhecimento é única. He worked as business development manager for some years in US, and he was product manager of the VNAs as well in Japan. So I spent some years there. So he have a lot of experience, plus 20 in worldwide projects, having a great background from the industry, research centers, and that will be shared today with his comments as well. And Professor Hugo, I'm glad to be here and make your presentation. You'll be the next presenting the LEMAC lab as well. He completed his PhD from Imperial College London in '92 and conducted postdoctoral research at University College of London, '93 to '95. So he has been full professor at Unicamp since 2005, where he leads the Applied and Computational Electromagnetics Lab, LEMAC, that we'll be glad to see here. So since 2011, he's an Optica fellow. His work is focused on the R&D and photonics and microwave devices applied to radars, telecommunications, and biotechnology. He has published more than 150 papers. So I'm glad to invite you, Hugo, to come here and present to us the LEMAC. Please. Thank you.
Thank you very much for your kind introduction. It's really an honor to be here with you and to receive this fantastic group from Anritsu. They are taking care of all the details to put our new acquisition, as Adriele mentioned, unique in Latin America. This is a VNA that operates up to 500 gigahertz, so half of a terahertz. And they are doing a fantastic work here, training and also taking care of all the details of checking, double checking this sophisticated system. Well, I am going to talk a little bit about our lab, and please. Presentação. Yeah, okay, this is a brief presentation. So we are part of the Department of Communications, the COM, and we are also part of the School of Electrical and Computer Engineering, ou em português, Faculdade de Engenharia Elétrica e de Computação. And of course, we are in the Unicamp environment. Well, this lab, Applied and Computational Electromagnetics Lab, was founded in 2000 by myself, and I am heading this lab since that time. So we are it's a 24-year-old lab. So a lot of history along these years. As I mentioned, we are part of our School of Electrical and Computer Engineering. This school, I am presently the dean of this school, so o diretor dessa escola. And this is in Brazil, our school also is special because we've been leading the rankings as the top electrical engineering school in the whole Latin American region for the last 15, 20 years, okay? At this very moment, we are 88 in the world, in the rankings. Okay. Well, what do we do at LEMAC? So we are mainly concerned with what is called the physical layer. Okay, it doesn't mean that we don't also develop software. So indeed, we do both, but we take a lot of care of hardware development. So electromagnetism is our battle horse. Okay, so this is our main tool, electromagnetism. So we are very much interested in developing always novel, unique devices, but in which frequencies? Microwave and photonic devices. So this is, when they say, the main goal of our lab. For what applications? Telecom and biotechnology. Okay, so this is a simple way to define what do we do at LEMAC. Okay, and of course, something else regarding our goals is miniaturization and integration. So this is something that we always set as an aim. Okay, so to miniaturize, to make something more compact. Well, this is our team. At the moment, we are two professors, myself and Professor Silveira, with Giliardi Silveira. He was my master and graduate student as well, a PhD student. And now he is an assistant professor here. And normally we keep an average of 3 postdocs, 8 to 10 PhD students, several master students, and several scientific initiations as well, so underground students. The facilities, we have essentially two labs. One in this building, in our electrical engineering school. This is the area of our lab, 120 square meters. And also in another building, in this building is close to the Physics Institute, and is a building in which all the photonic activities at Unicamp are concentrated. So we call this building Photonic Camp. So in this building, we have another lab of this, occupying an area of 80 square meters. So these are the equipments we have in our labs. Here we have now 3 network analyzer of 20, 40, now 500 gigahertz, one anechoic chamber, and several high-performance computers. Okay, and then at Photonic Camp, we have a fully equipped photonics characterization facilities, 4 optical tables, and all these equipments operate in the optical communication bands and also in the visible, especially for biosensing. So our lab is also part of large scientific projects. At this very moment, we are part of these 3 large scientific projects. CPT, which is the Paulista Center for Energy Transition Studies. So I coordinate these axis, 8 smart counties. So we have 3 sub projects here: connectivity, sensing, education, smart communities. And we also are part of the smartness, smart grids and services towards 2030, and also this multi-user equipment project. In this multi-user equipment project, we have fiber and wireless communication test bed. So our VNA has been acquired with the financial support of this project. So especially for the wireless communication applications. So we are here, we are very much concerned with high rates and wide bands solutions. Okay, so this test bed is being implemented, and is going to be also a unique facility in the Latin American region, and probably in the Southern Hemisphere. Okay, and of course, it's going to be open for the whole community. So if you are interested in performing tests, or or even joint projects with us, we are very much open for that. Okay, I am going now briefly to talk about 4 projects. We have more projects, but these are, let's say, our current projects and quite emblematic projects in our labs. Okay, but of course there are other projects going on in our lab. But briefly, I'm going to tell you something about this technology we have developed in our lab, which is an airborne drone synthetic aperture radar. Of course, this can operate as a radar to collect data above the ground, but also underground. Okay, so underground tomography. Okay, so in the lab we have developed all the details, from the hardware even to the software. Okay, recently, for instance, in software, we developed fast back projection. Back projection is imaging processing software. Okay, and recently, this was a PhD thesis of a student of mine, and she was able to produce this fast back projection, reducing the CPU time in almost 2 orders of magnitude. Okay. Well, there are many publications related to all this. You can find this easily in the literature. So, this is the detail of this. This is a 3-band radar. It operates in the P, band, it's about 400 gigahertz, L band, 1.2 gigahertz, C band, 5.5 gigahertz. So this is a motherboard. This is the heart of the system, okay? And you can see the C-bands antenna embedded here as part of the motherboard. So there are two sets of antenna, two arrays, so we can perform in-SAR processing as well. The P-band antennas and the L-band, okay? Well, so what is new? Of course, the question is, well, what is new? Well, because this technology is already known and is being in the literature, in the market, since the 1970s. So, but what you find in the market are systems like this operating but before to use this synthetic aperture radar, you need movement. It's essential but to have movement. So the radar must move. Okay. Well, this is so what you normally find in the market are these systems transported by satellites and by airplanes. Okay. So what we've done here is to shrink these conventional systems that weigh 80 kilos, 90 kilos to less than 5 kilos. So this is the achievement. Okay, then why? You say, well, because we want to use drones. Okay, and then what is new using a drone? You may say, but what is new? Well, what is new is that you have a new degree of freedom, which is the trajectory. Because as I mentioned, movement is very important in this process. With the movement, we can emulate large antennas. This is synthetic aperture radar. No? So with this process, you can emulate very large antennas. Okay, so with your physical antenna, you may have a kind of poor directivity. Okay, but using SAR, you can improve. You can emulate this antenna. Okay, with the movement. Okay, launching pulses and receiving these pulses and integrating these along the time, so you can emulate a large antenna. So, the larger the antenna, the narrow is your beam. So you increase directivity. Okay. So if your fly is linear, so you are going to increase, okay, your resolution. So you are going to have a long, you can emulate a long antenna. So the resolution you improve is along the azimuth direction. So the velocity vector. Okay, so along this direction only, because in the other directions you rely on your physical antenna, on the directivity of your physical antenna. Okay. Well, but what if you perform a circular flight? So you can improve your resolution in all the 2D directions. And what about a helical flight? With a helical flight, you can improve your resolution in the 3 dimensions. Okay, so this was also a thesis, a PhD thesis recently defended. So with this result, we are opening a new research frontier, which is the underground tomography. So we can then reach the physical limit there, because there is a limit in this resolution, which is λ/4. Okay. Well, of course, there are many applications for this kind of technology, plagues detection, unmasking industrial fires, mining, agriculture. Well, we are involved in projects that are connected with these applications. Okay, so just to illustrate and to show you some results, I'm going to choose this one. Okay, or before. Also, this is an above ground um, result. So this is a moisture image, a moisture map. So this is also a unique product of our system. So this provide a moisture map. Okay, so normally to get this kind of maps in agriculture is cumbersome. It demands manpower because people need to sample the ground, sample the ground to measure in the lab the moisture. So with this system, you can provide a map. This is something special. This is something special. This was a project funded by FAPESP. It was a PITE project with the partnership of IBM and also the San Martino group. These are applications in the industrial forest. So this is also a moisture map. Okay, these dots here, these red dots you see here are the trees. So you know, in the trees you have more water. Okay, this is why the maximum humidity is in these dots. Okay, and you can see even the shadow of the tree. Well, so in the normally, of course, we perform always a very rigorous comparison with the field measurements and the radar measurements, and the resolution of these measurements are typically less than 10% or something like that. Then this was really a challenge working with Clavin, because these ant nests are really, they impact this industry a lot. The impact is almost 15% of the production. Okay, so this is really last week I was in a forest conference in Curitiba, so they invited me to talk about this. And people, they went crazy because they were talking about possible solutions. I thought about the solution. It's different. Okay, so our system with the P-band always goes through the vegetation. Doesn't matter if the vegetation is very dense, doesn't matter. It goes through, underground. The L-band depends on the vegetation. If there is no vegetation, of course, L-band also penetrates nicely. But the C-band always is reflected on the top of the vegetation. Okay, so you can imagine if you have this information, the dosel of the vegetation, and you have a very good measurement about the ground level, you have the volume, and then from the volume you have biomass. You have a lot of figures of merit that are really very valuable for precision agriculture. So, well, this is just to summarize this. We use artificial intelligence. So we train our machine learning algorithm using areas in which we already knew the position of these nests. Okay, and then after that, we were able to find in a different environment, the nests. Okay, so the error was is about 3 meters, which is really very, very good if you take into account the areas of these industrial forests are several hundreds of hectares. So it's really something. But not only that, once we identify the position of these ant nests, we perform the underground tomography. And this is what we get. So this is the tomography. We can also get this information about the volume of that. This is unique. I can tell you, this is unique. Nobody, as far as I know, in the world is capable to do this, to provide this kind of information. Well, there are other projects. I'm going to just go very fast here. Of course, we also work with nano-antennas. We also developed several techniques to find to do inverse, to solve inverse problems, in which you know the input, you know the output, and the question is what you can put in between. So you can, for instance, use this technique, now topological derivative, and then, for instance, in this case, we want to find an antenna which is fed but waveguide, optical waveguide, in this case silicon photonics, silicon waveguide, and we want to know the geometry of this antenna, okay, of course to fulfill some features, okay, so with this kind of algorithms, you can find solutions which are regarded as non-intuitive solutions, because it's difficult to associate to already known geometries. Okay. So this is, for instance, the smallest nano antenna so far, I should say, in the world, the smallest one. Okay. So in silicon photonics. Of course, with this antenna, you can perform several applications. For instance, now we have a project developing fully integrated photonic beamforming for LiDAR applications, especially because so far to have a fully integrated LiDAR is still a challenge. Several labs are working on that, trying to get a chip. And in this chip, to have a single LiDAR, indeed. So this is a challenge. Well, we are working on that. Of course, this is but in order to get only a single beam, so we are proposing this kind of a periodic array. Okay. And this periodic array follows a pattern related to a Fermat spiral. Okay. Well, there are several publications, so if you are interested, you are welcome to talk with us. One of the main applications or features is the very large field of view. So you can make this steering almost covering a half hemisphere, completely half hemisphere. Well, this is another interesting result here in our lab. Well, so we've been working with non-reciprocal devices. So, and then we have also produced the smallest magnetic photonics isolator. Okay, this was carried out in partnership with the Tokyo Institute of Technology. So also the MAC has a very wide international network. So we keep several international projects. Recently, we are working with a group in France. We have other connections with Germany, UK, well, several groups, China as well. Next week I am going to Germany because of this kind of collaborations. Well, non-reciprocal devices, probably you know, but if you have, for instance, this situation, and you excite this port, it's a 3-port situation called as a circulator. If you excite this port, then you couple your mode to this other port. And if you excite this one, you excite the output is in this port, and the same. So it follows the one. So what is not reciprocal, because if you inject, for instance, your this port 3, the output is not port 1. Reciprocally speaking, this is what you expect. You excite port 1, if it goes through port 3, then if you excite port 3, the output should be port 1, but it is not. The exit is port 2, and it follows this sense, rotation sense. Okay. Well, one application is, for instance, one antenna as a duplexer. So you can use one antenna to connect a transceiver and a receiver, only one antenna. So you need a circulator here. You need a non-reciprocal device here. Okay, so this 3-port can be also used as an isolator. So an isolator, what is the main function of an isolator is to avoid reflections here. If you launch your signal here to feed this load, then the reflections go to the other port. So you protect your instrument here or your source. Okay, so the idea is to, what we have in the market normally are very bulky isolators, because they need an external magnet. So to make this integrated, we need to avoid the external magnet. Okay, and then what we've been using is materials, special materials, which they preserve the magnetism. Okay, so you can apply the external magnet, and then it keeps for a very long time. It keeps magnetized, this material for quite a long time. Okay, so we call these magnetless optical devices. Okay. So, well, this is simulations, etc. So this is a resonator, and then we were able to fabricate this. So this is the real thing, okay? And of course, we measured, and indeed it works. It works as an isolator, okay? So it means that if we, just to let you know, so we have 2 frequencies here. We can use these 2 frequencies. Okay, so if we use, for instance, this frequency 1, and if we excite in port 1, all our power here, electromagnetic power, go through. Okay, because the excitation is weak. Okay, but if you excite from this port, the excitation here of this resonator is very strong. Okay, and so it prevents this mode to go through port 1. So this is, and of course, if you change the frequency, you can have another port as an isolator. Okay, so in comparing this as well with other solutions, current solutions, and these solutions are still lab solutions, so are not our commercial solutions. Okay, so the difference in terms of footprint is almost two orders of magnitude. This other project, this project has been carried out with this collaboration with the NanoBoom. It's interesting. It's a nanotechnology lab in the Basque country in Spain. here, in few words, what we try to do is to use nano antennas as a sensors. Okay, I'm going to be real more concise here and to explain what we can do with this. This is the real thing, a prototype, but this is the idea of these nano antennas. So we excite these nano antennas, and then these work as resonators, and you have a transmission or a reflection, and then you can use this system, for instance, to measure the neuronal activity, because the neurons, when they are alive, they have an electric field. The electric field oscillates in a low frequency. So the main goal is to measure this electric field activity in a cell. Okay, so how to do that? So we were inspired by the optical communications modulation. So if we are able to modulate the field of this biome sample to a carrier, this can be a way to do that. So essentially, this is what we have done. So this is the nano antennas. We put on top of this biological sample. Okay, for instance, neurons from the brain. And so these neurons, they emit an electric field. Okay, so this electric field is going to perturb the resonance of these nanoantennas. Okay, and then it's possible to, with this perturbation, to modulate the transmitted or reflected beam. Okay, so we've done this. This is the PhD thesis of a student of mine, of Ursula. And recently, we've been able to measure, this is the electric field of the neurons of a rat heart. Okay, so we are, of course, writing a paper about that, about this technique. Okay, so this is also a very interesting, unique result. Well, this is it, just to let you know some of the activities we are carrying out in our lab. Thank you very much for your attention.
Now we have a video with about the LEMAC laboratory, and after this video, Arno Petai will start his presentation around that system that Professor Hugo mentioned. Thank you.
Hey, boa tarde. Good afternoon, everyone. That's about as much Portuguese I know. Just a few other words, and that's about it. My name is Arno Patai, and I think Adriela gave a short bio on myself, but I'll just throw in a little bit of extra here. I've been in the industry almost 40 years. Next summer will mark 40 years since I started working. I was working in aerospace and defense for a few years, then in satellite communications. But I have spent the bulk of my career in test and measurement, and almost all of it at Anritsu. I had a small sabbatical, I'll call it, when I went to another company that used to start with A. I'll leave it at that. But I've been with Anritsu 24 years, which is also interesting that Lemac was founded by Professor Hugo in the year 2000, as the year I joined Anritsu. So 24 years I've been with Anritsu. And as Adriele mentioned, I've been a product manager for VNAs, not just this VNA, but the one before that. And I also spent 3 years in Japan, helping with the business development of our US-based products into the Japanese market. So while Anritsu is a Japanese company, and we are part of that, we're a US division that's part of Anritsu, specializing in RF and microwave instruments. We're part of a larger company that does a lot more in test and measurement, including optical and wireless and high-speed digital. But I spent 3 years in Japan to support the US division. And that was truly one of the best moments in my career. Really enjoyed that. What I'm doing now is number 2. But after about 18 years as a product manager, I decided I wanted to spend all my time doing what I do best, which is in front of customers, talking about Anritsu products, learning about challenges that our customers face, and helping solve those challenges with solutions that we have to offer. And so I decided to devote myself to the field. I moved out of product management, moved out of the division, and went out to the field 6 years ago. And that's what I have the most passion for doing. And so I just cover mainly the West Coast of the US, but because I'm the principal application engineer in the factory in Morgan Hill, California, where we design and build these instruments, I also cover it in the US and the wider Americas, including South America and Central America. So I'm very honored and privileged to be here with you today. This is really the conclusion of a fairly long trip I've had, 2 weeks in Brazil, to primarily be here to install this new VNA system in the lab, in the Lemac lab, which includes the 220 gigahertz single sweep and then the additional bands in waveguide to get to 500 gigahertz. It's truly a unique system and the first of its kind in all of Latin America, and very rare pretty much anywhere in the world. We have sold other 220 systems, and I'll talk about that and where they are, but this is a unique achievement. All right, I'm just going to quickly mention that the division in California is responsible for general purpose RF and microwave. And that includes, most importantly, is VNAs. That's probably the most complicated instrument on this list. But also we make microwave signal generators, power meters, sensors, many of the accessories that go with VNAs, components as well. Very important part of a microwave engineering bench is to have components that you can use, cables, connectors, adapters, bias tees, etc. And then we also have a whole range of handheld battery-operated instruments used in the field for spectrum analysis, cell site testing, cable and antenna testing. So that's a whole nother range, but related to VNAs, because at the end of the day, they're stimulus response systems that provide a signal, and we measure the signals coming back, and we're able to analyze the performance of these systems in the field equally well. So of course the performance requirements are different in the field versus in the lab, but technically they're the same functionality. Okay, so that's the US division. We're based in Morgan Hill, which is south of San Jose, south of the Bay Area, Northern California, for those of you who know that part of the world. I live in San Jose, and I'm about 15 minutes away from the division. All right, so we're going to cover a wide range of topics related to VNA. So we're really going to be talking only about the laboratory VNAs that are used benchtop in R&D, sometimes also in manufacturing. I'm going to start with a brief primer. How many of you in this room feel comfortable using a VNA? Give me a show of hands here. Oh, okay, more than I thought. That's good. I'm going to just give you a brief overview, so those of you who are less familiar will kind of understand the basics. These days with VNAs, there's a lot more that you can do than just the standard S parameter measurements, but obviously that's the reason why VNAs exist. Then we're really going to dive into some of the topics related to this system that's here at Unicom. All right, the 220 gigahertz single sweep system. And we're going to look at some of the focus applications for a system like this. You know, we have device characterization, for example, that makes use of broadband measurements to characterize devices and build parametric models for circuit simulation. Then there's also the whole topic of optoelectronics. You know, once we've got these high-speed, high broadband, high bandwidth devices, some of them are not just electrical, but also have optical or cross over to the optical domain. So we need to look at how to characterize those devices as well. And then we talk about high-speed serial interconnects. That's a very important area, again, for broadband communications. And some of this area here goes more into the differential side of signaling, not just the single-ended, but also the differential, which really is the case for a 4-port VNA versus a 2-port VNA. And then if there's time at the end, you know, there's a lot to cover here. We'll look at some of the active measurements too that are possible with the VNA. Most of what we're going to talk about is mainly passive, but we will look at some of the active stuff at the end, as long as we have some time. Okay, and at any point in time, if anyone has any questions, both here in the room and out on the remote side, go ahead and ask the questions. I'm very happy to have an engaging conversation here about these topics. All right, so let's start off with just the basics of the VNA. I show you the block diagram. It's very important to understand that we're talking about a stimulus response system. Unlike a spectrum analyzer or a power meter that's basically measuring a signal, we're actually generating the test signal and we're measuring. We're measuring what gets reflected back and we're measuring what gets transmitted through. We're interested in characterizing a device for its reflection and transmission characteristics. And we place that device between the 2 ports so that the device receives the stimulus, something gets reflected back, something gets transmitted across, and through these reflectometers, which are directional couplers essentially, we're able to separate the transmission from reflection signals and analyze them independently. And we also have a couple of receivers that are dedicated for just grabbing a reference. So we know what we sent in the first place, and then we measure what comes back through these other receivers. So the A receivers are reference, the B receivers are test, both directions, forward and reverse. So that's our primary concern, is to measure transmission and reflection characteristics, or the S parameters. Magnitude and phase, this is a VNA, not a scalar analyzer. So it's a vector, so it's magnitude and phase. And then we have other measurements that are possible using a VNA, modern VNAs that have more hardware, like a second source or ability to sweep power instead of just sweeping frequency. We can look at gain compression, IMD, and these are many of the active topics that we'll cover at the end that require that additional hardware, that require that second source, that require the ability to not only sweep frequency, but also power, that might need additional hardware for measurement of those signals. So we'll look at that. But in general, VNAs are swept frequency response, stimulus response instruments. We have a source, we have receivers, we have reflectometers, and we have a switch to be able to go from forward to reverse. So this is one of my favorite things. If I was to describe what's the difference between a VNA and a spectrum analyzer. A VNA measures known signals because we're generating them in the box and we're sending them out to the device. So we know what we're generating. We know, therefore, what we're going to measure. But in the case of spectrum analyzers, you could get a little both. You might have signals that you know are there and you'll find them, but you're also going to find signals that are unknown that you didn't know were there. VNA is not designed to do that. VNA is designed to measure known signals, whereas a spectrum analyzer or a power meter would be doing both known and unknown. So that's an important distinction between VNAs and spectrum analyzers. A VNA can behave as a spectrum analyzer, but its receiver is never going to be as good as the standalone spectrum analyzer because it doesn't have the same capabilities. It's not designed for that initially. It was designed to do ratioed measurements. This is being used here when you're a spectrum analyzer to make absolute measurements. So again, the receiver detection is different between the two kinds of instruments. But I always like to point that out because most people are very familiar with the absolute measurements that you make in dBm, power. But here with the VNA, we're primarily concerned with ratioed measurements where we know what we're sending and we measure what's coming back, either reflected or transmitted. And we do a ratioed measurement. And when we do a ratioed measurement, we end up with dB. So VNAs measure mostly dB. Spectrum analyzers mostly dBm or dBc or something more on the absolute level versus the relative level. All right, so why do users need VNAs? Well, it's very simple. We have to characterize RF performance of devices, components, maybe even up to a subsystem level where we have some path that we need to characterize, transmission, reflection. We do this in the lab, we do this in manufacturing with VNAs, and also with the handheld instruments I mentioned earlier, we can take that out into the field and do maintenance of cell sites and other remote installations. Most of the challenges we face are going to be with what is the packaging, what is the input, what is the output, how do we adapt our VNA to be able to measure these various types of interfaces. Most of the time, it will be coax, and we all understand coax. We're going to have some kind of cal kit that we can use because I'll tell you why you need to calibrate in a moment, but we need some kind of cal kit to be able to calibrate our VNA so that we can make these measurements without including anything else that's in the measurement system, because we want to isolate our measurement to just the device that it is we're interested in. So most common is coax, but then we have a lot of other interfaces, waveguide being probably the second highest that we see, and then devices that have no connectors that are either in a fixture or on a wafer substrate. So we have to adapt constantly to these different interfaces through the way we set our reference plane and our calibration. And I'll explain that in a moment, but that's one of the key things about how to run a VNA measurement. It's not just stick the signal into the instrument and measure it. It's you need to understand everything that's in the measurement path and know how to interface with it and isolate what it is you want to measure out of everything that's connected. And we'll talk about optoelectronic. That's really a new area for us because we're crossing into optical domain and we need to characterize some of these devices also frequency across the frequency domain as they convert from optical to electrical back to optical, or the other way around. S parameters, probably the most popular measurement with the VNA, the reflection parameters and the transmission, both forward and reverse. So these are your S parameters. But then again, with the additional hardware, we can look at a lot of other measurements that are more on the active level that are utilizing additional hardware, and other instruments can do these jobs as well. But it's nice to be able to put a lot of this into one instrument so that you can get a second opinion on things and have a second way of analyzing some of these same parameters. So we have to test a lot of different devices, both active, passive, and then we have high-speed interconnects and antennas, transmitters, optical modulators, and receivers. So you can just see there's just a very wide range of things we could do with the VNA. Something to bear in mind. One of the most versatile instruments on the RF and microwave design engineer's bench. Now, calibration. This is a topic that is a little bit different for the VNA versus the spectrum analyzer or the power meter. Every instrument gets sent to a cal lab to be calibrated, and you get the sticker and you get the calibration certificate for that. But in the case of the VNA, it's a step further. We'll get that calibration done for power and frequency, but beyond that, it's really up to the user to do the calibration that's required to make an accurate measurement. Because without the measurement calibration that the user does, you can't get a good result at all. And every user is a little bit different. No two users I've ever met for VNAs are exactly alike. So the amount of care and technique that each one provides to this kind of process is very important to the result of the measurement. So we need to calibrate the VNA to establish what is the 50 ohm reference, because all our measurements are going to be referenced to some impedance standard. Maybe not necessarily 50 ohms. It could, in some cases, be something else. But again, the cal kit is what determines what the reference impedance will be. And most cal kits are 50 ohms. We also want to establish the reference plane. And what is the reference plane? Reference plane is where we want the measurement to start and where we want it to end. Everything else we don't want to have included. We have occasion to use either a manual cal kit or automatic calibrator. Automatic calibrators generally only up to 70 gigahertz, nothing higher than that, because the frequencies and the parasitics and the components just doesn't lend itself to making automatic calibrators. So generally we're using manual cal kits at high frequencies, whether it be coax or waveguide. And then we have certain calibration methods, or call them algorithms, that are run to be able to perform this error correction process. And most popular is the SOLT, or short open load through, but there's also other calibration techniques like line reflect line, line reflect match, that are also used in VNA calibration. All right, calibration, again, as I said, is fundamental to making any accurate measurements with the VNA. Without it, all bets are off. Measurements are raw and not corrected, so they're not accurate. So calibration is essential, and we want to establish where we want our reference plane to be, so that when we measure the device, we don't include these cables or anything else that's non-ideal about the instrument. No instrument is perfect, so that's why we do this. No cable is perfect, so that's why we calibrate, is to get all of these other contributors characterized and removed from our measurement system. So at the end, we're measuring between this red dashed line and this red dashed line, and we're only looking at the device that we're interested in. So we're setting our reference plane up to be 0 dB, 0 degrees phase. We're going to remove all the systematic errors that are related to the instrument, which include things like source and load match, directivity. You know, no instrument is perfectly 50 ohms at its test port. No coupler, directional coupler, is going to be perfect as far as directivity, so there's always going to be some leakage in the other direction. And we need to quantify those things and remove them from our measurement. And that's the whole process of error correction, is to do that. Isolation, less important in today's modern VNAs. There's less leakage between the two ports. That used to be an issue in the past. But it is part of the 12-term error correction model. We're basically gathering all this information to apply what's called error correction. And it's a 12-term error correction that includes all of these contributors. Transmission tracking, reflection tracking, they're all part of that 12-term model. And many of these will influence your measurement accuracy, but also how well your calibration behaves over time and temperature. That's another thing to consider. If you have poor cables, for example, you're only going to hurt yourself then later because there'll be drift, because these transmission and reflection tracking terms are going to drift as the cable changes over time and temperature. So it's very important when you're using a VNA to have good cables, not only a good cal kit, but have good cables as well. Now, we do have some errors that are impossible to completely remove because they're related to things that are more random in nature. Things like connector repeatability. I mean, every time you made a connector, it could be slightly different. We try to control that by using a torque wrench, but it's not always possible because these connectors wear out over time too, so their repeatability can suffer. I mentioned cable stability. That's crucial. That's 9 out of 10 times when somebody calls me and tells me their measurement is no good, my first question is, what cables are you using? I'm not even concerned so much with the instrument nor the device they're testing, but the cables tend to be the problem 9 out of 10 times. That's causing drift or causing something that's intermittent. And then environmental changes. Yeah, we can control the temperature of the room as much as possible, but there will still be some changes. Obviously, you want to keep the instrument on long enough so that things stabilize, but they're going to drift over time and temperature. And so those are things that we just try to control, but you can't completely eliminate. Cal kits. I mentioned you have to calibrate. Well, what do you use to calibrate? You use cal kits. You can use a manual cal kit, which is this one, with all the open short load standards inside. That's a coaxial kit. There may be a waveguide equivalent to that we would use for waveguide interfaces. Again, a manual cal kit. We have automated cal kits to 70 gigahertz that are coax that can be used with the VNA. These are nice if you're doing manufacturing because it helps remove some of the repeatability. That is a concern when different users do the calibration. They have different technique. The AutoCal helps level that a little bit so that you get similar results every time or close to every time. We have microstrip cal kits. You can see these kinds of substrates that fit into a fixture. So if we're doing measurements where there are no connectors, it's just a substrate and I have a specific fixture to use, or on wafer. On wafer also makes use of substrates that have the same standards that are here, but on the substrate, etched onto the substrate. And so we touch down on the various standards to complete our calibration, whether it's in a fixture with some jaw mechanism or on a probe station with real probes. And we'll talk more about probing in a little while. So that's all for the relative or ratioed measurements that are classical with the VNA, so the S parameter measurements. But as I mentioned, we have advanced measurements that we do now for active devices. And so those are going to require different ways of calibration because now you have to calibrate the VNA instead of measuring dB, as is the case with these measurements and the ratioed measurement. You need to now look at absolute measurements in dBm. And so I need a power meter to do that. So I have to train the VNA receiver on what is an absolute power level. So I first calibrate the source to a certain power level, and then I use that calibrated source to train my receivers to measure also in an absolute sense in dBm. So that is the purpose of the power meter, is to basically perform that source calibration, and after the source calibration, the receiver calibration makes the receiver able to measure absolute rather than the normal task of doing ratioed measurements as we did here. So that's for the gain compression, IMD, harmonics. There's a few other cases, noise figure, other cases where you need to measure in absolute terms. You need a power meter to do that. Finally, E to O and O to E measurements require an O to E reference. You need some way to be able to separate E to O and O to E. And the only way to do that is to have a reference for one or the other that you can remove when you're measuring the two together. Because the VNA is going to start with electrical, it's going to end with electrical, but in between you could have an E to O and then an O to E. Well, I need to know what the response of one or the other is so I can effectively remove it and make a measurement of the opposite device. Isolate it to what you want to measure. And the O to E module provides that reference because it's a characterized photodiode that has magnitude and phase information up to as high as 110 gigahertz. So we use that as our reference. Okay, any questions on kind of the basics of VNAs, the primer, as I like to call it? It's all pretty simple stuff, I hope. All right. Now we're going to move on to the Anritsu VNA, and the applications associated with the broadband and millimeter VNA. But I did want to point out that we have other VNAs in our product portfolio that are used in manufacturing, for example, that don't necessarily reach the terahertz or sub-terahertz or millimeter wave levels. These are RF VNAs that are microwave VNAs up to 43.5 gigahertz, same down here. And you can see many of our handhelds show up in these pictures as well, because they cover frequencies into the microwave range, but used in the field. But again, doing very much the same kind of measurements, reflection and transmission. And then this one here is very unique. You're probably wondering, well, what is that one with all the long cables attached to it? It's a distributed VNA. So think of a VNA, 2-port, like this one here, or this one. This is a 4-port, or the vector star. What if we sliced that VNA straight down the middle and broke the 2 ports out on their own and provided an optical phase interconnect between the 2 sides? We can do the same measurements as we do with a benchtop 2-port VNA, do it in a distributed way. Where would that application be? In a chamber, perhaps. In an aircraft. In a ship. Someplace where the cable that you want to measure cannot be moved. So you need to bring the instrument to the cable that you want to test. Well, if you take the benchtop VNA out there, you have to attach long cables to get to where your cable is that you want to measure. Well, instead of doing that, instead of adding long cables to a traditional 2-port benchtop, move the ports themselves out to where you want to measure, but provide the phase synchronous behavior. You need to have the phase coherence between the receivers. Otherwise, you can't make transmission measurements. You need to be able to ratio these 2 receivers in a phase coherent way. But we're able to do that with these optical interconnects and this controller in the middle that essentially fans out those signals to both sides, so that we have the LO and the reference that we need on both sides. So it behaves just like a standard 2-port like this one or this one, but it's distributed. It's a unique concept. You probably have never seen anything like it, but it's something that Anritsu has come up with for these very long distance applications, like in antennas and on aircraft or on ships. But it's operating just like a regular VNA. We have a PC that's used to run it. It's running a similar interface to what's on the vector star. But now we're going to just really concentrate on this high end here. So the mainframe VNAs up to 70 gigahertz, and then the extensions to broadband and millimeter wave. All right, so on the vector star, we have basically 3 what we'll call baseband models or mainframe VNAs, 2-port VNAs, 20 gigahertz, 40, and 70. The most popular one is the 70 because it's really the basis for higher frequency systems, because you don't want any gaps. So if you're going to do a broadband system like the 220 gigahertz broadband system here at Unicamp, you need to start with the 70 gigahertz to be able to upgrade to these higher ranges. So that's our top selling VNA is going to be 70 gigahertz 2-port. Then we can add extender modules like these and the test set that provides the RF and LO to the modules and allows us to get up to as high as 220 gigahertz. So everything that I show you here is building blocks. So you start with this basic unit, you add a test set to expand to 4 ports, or you add a test set to expand to millimeter wave broadband, or you combine them all together and make a 4-port broadband system. So everything is possible here. There are no upgrade paths that can't be accommodated. Now, above 220 gigahertz, where we have our single sweep systems, we have the banded ranges up to 1 terahertz. So the system here at Unicamp has the single sweep 220 plus 2 bands to get to half a terahertz, 500 gigahertz. With the VNA, there's a lot of different options. Of course, certain options are important if you're planning an upgrade in frequency later on. Most of these are actually software. There are a few that are hardware, and obviously important to understand if you have an upgrade path, like the broadband millimeter interface. That's really what determines whether we can upgrade higher in frequency, or the direct access loops or the active measurement suite are important if you're going to add on the 2 ports, the 2 additional ports for a 4-port system. That ties in through the direct access loops. But many of the rest of the options are primarily software. So time domain, the ability to offset tune the receiver to a different frequency from the source. That's what's called receiver offset. That's important too for the millimeter wave system, because we're essentially operating with frequency converters when we use the millimeter system. The other hardware options that are worth noting are the second source, which is important if you're going to do IMD measurements, or some of the differential true mode cases also need the dual source. The internal combiner is also for IMD measurements, where you need to actually take the 2 sources internal and combine them and present them to 1 port. Because if I'm going to make an IMD measurement, I want my stimulus to be on the port 1 side, both tones, and then I can measure IMD. So those are some hardware options. So these 30 options, these 3 series options are hardware. We also have an IF digitizer if you're going to do wider bandwidth receiver measurements, like pulse test parameters, because it's going to be wider bandwidth, wider analysis bandwidth than a typical VNA, would require the digitizer to do that. So that's also hardware. Everything else down here is software. These are all software personalities for adding specific measurement capabilities, everything from a spectrum analyzer to the IMD that I already talked about, or an eye diagram simulation. TDR is covered under time domain, so that's another area of interest often, is to do a time domain reflectometry and actually see what your impedance is along the line. But that's part of time domain. Then in addition to the options, we have all the cal kits, we have the power meter sensors, cables. See, we'll sell you good cables if you want good cables. So we're mindful of that. So that's why we put that there, because we like to sell all the accessories, right? Adapters and biasing. We make a lot of components at Anritsu. So I like to think of our division in California as not just an instrument company, but also a precision component company. Because quite frankly, you can't make high performance instruments unless you have the component technology to do it. You can't go and buy these things off the shelf. So we are able to create our own, basically, components for high performance to insert into the instruments to maintain the performance we advertise. All right. So let's start with the basic unit, which is a 2-port VNA. I call that the baseband VNA. We're covering from as low as 70 kilohertz. And I'll mention why we can get to 70 kilohertz in a moment, because most microwave VNAs don't go down that low. You have to use a different VNA to get there. And then we're going as high as 70 gigahertz in the single box here. So a baseband VNA does not require additional frequency extenders. Everything's built into the box. All the hardware for the reflectometer, the source, the switches, everything is internal, up to 70 gigahertz. We use different connector types depending on what frequencies we're covering. So if it's a 40 gigahertz instrument, we're going to be using 2.92 or K connectors. And if it's a 70 gigahertz instrument, it's going to be 1.85 or V. So this is what we start with. This is the first part of our system, is the baseband VNA. The only way we're going to get that kind of frequency coverage from kilohertz to gigahertz is to separate the architecture inside the VNA. So we have what really resembles, and I'll show the block diagram in a moment, a microwave VNA and an RF VNA all in one box. And we use a combiner a passive combining approach to bring the two together and present them at the test ports. Most microwave VNAs, certainly our previous generation and others that are on the market, generally start at 10 megahertz. With this option and the additional hardware that's already built into the unit, every unit we build is capable of going down to 70 kilohertz. We can cover the full frequency range of an RF VNA and a microwave VNA. This is truly unique. Most of the time we had to use 2 VNAs to get this coverage. So we have to separate the component technology that we use in both bands as a result. We can't use directional couplers at low frequencies. We can't use mixer-based receivers at high frequencies. So we have to basically split the architecture into 2 equivalent architectures, one for the low band and one for the high band, so that we can cover the full frequency range. And then we have the combiners here. These are basically diplexers, passive. It's not a switch. That's very important because this is passive, so we can properly calibrate our VNA and not have any drift. This is what brings together the 2 bands. So the low band here, which is everything below 2.5 gigahertz down to 70 kilohertz, and everything above 2.5 gigahertz is in the high band and utilizes more traditional microwave VNA architectures. But on a block diagram level, they look the same. It's just the components that are different. But it's what allows us to combine the 2 bands into one and go from 70 kilohertz all the way up to 70 gigahertz. But again, we're still talking, that was still the mainframe or the baseband VNA. Now we're going to take it a step further by adding the test set, the millimeter wave broadband test set that provides the interface to our frequency extenders and allows us to upgrade to 125, 145, and 220 gigahertz single sweep system. So the broadband VNA consists of the mainframe and the test set, and we want to keep things coaxial. Why? Because we would otherwise have performance issues. We would have moding and other issues to deal with. So we need to have the right connector type that can take us all the way up to the high frequency while still maintaining the low frequency performance. So if it's a 110 gigahertz VNA, naturally we're going to use something like a 1 millimeter test port. If it's higher frequency, we're going to have other connectors that are still coaxial to get us the performance we need without any gaps in frequency coverage. So for the broadband system, currently we have 3 different bands, up to 125 gigahertz in 1 millimeter, up to 145 in 0.8, and up to 220 gigahertz in 0.6. Now you might look at those pictures and say, what's different between them? Well, the connector is different. 2 of the models have threaded connectors, which are kind of more traditional that we're used to. We have CalKits that are threaded, we can use with those. But the 220 gigahertz is a 0.6 millimeter coaxial pin. It's like a coaxial waveguide, actually. It doesn't have an outside threading. So the way it works is we have a pin and a socket system, 0.6 millimeter, but it's inside a waveguide flange. So you'll see the alignment pins here that resemble a waveguide. And your first thought might be, oh, it's a waveguide system. No, there's actually a pin inside the small little opening in the front of the module that's 0.6 millimeter. And it's that interface that we use to connect whatever it is we want to add to the system, whether it's a probe, whether it's an adapter to go back to a waveguide flange or to a 1 millimeter. We can adapt the 0.6 back to a 1 millimeter. We can do the same with a 0.8. But if we want to operate at full band, up to 220 gigahertz, it has to be the 0.6. So it becomes a little bit challenging how to work with an interface that doesn't have threading, right? We're not used to that. But you can't make a reliable, repeatable, threaded connector at 0.6 to get to 220 gigahertz in a single sweep and not have bands that drop out. Right, so basically all of these things apply. We have the single sweep coverage, We have the calibration stability, since we're not using anything external to the module. Everything's internal to the module. That helps us achieve better calibration stability over time and temperature. Very important if you're doing calibrations on wafer. Who wants to do calibration every hour? You know, it's very complicated when you're on wafer. So again, having no external combiners like we used to have in the older generation systems would only add to more drift over time and temperature. We have built-in closed-loop automatic level control. Why is that important? If you're testing devices that have gain, you may not be able to use the full default level, and you may need to adjust the power level down so that you don't saturate the device. And so that's what automatic level control provides. Not so important for passive measurements, but very important for active cases. So this is also unique because in the past we used to have to use a waveguide attenuator, you know, with a dial to make these power levels. Now we can do that electronically and get it all inside the same module with what was formerly an external combiner internal to the module as well. So in most cases, given the size of these modules, they're basically the size of the palm of my hand. They fit right there. We can get the module to where we want to apply the signal, which in most cases is right at the wafer probe. So we avoid adding more cables. Remember how earlier we were talking about the distributed VNA, and I said you don't want those extra cables because those only add loss and create stability issues. Same thing is true here. But now instead of talking about microwave frequencies where these cables were that long, now we're talking about millimeter wave frequencies where even this length of cable becomes an issue. It's a half a dB per inch, typically, for these cables. So you can see as the losses add up, you're taking away from the dynamic range of the system. So that's why at these frequencies, it's absolutely critical to have short cables. This is just to show you what the different signals are interconnecting between the mainframe VNA, the top unit here. We have to supply the LO to the receiver inside the two modules. There's two separate LOs, one for each side. There's an RF that's generated and gets multiplied up in the modules, and I'll show you that block diagram in a moment. But again, all of these signals that we need for the source and for the receiver are generated in the mainframe, and they're carried through the test set and conditioned. There's some signal conditioning that takes place. But it is the interface unit. So the box that was underneath the mainframe is really the interface unit between the mainframe or the baseband VNA and the 2 millimeter extenders. The IFs are also returned from the modules. So the reference and test IF are also returned via the test set to the mainframe. And they bypass the mainframe receiver because you don't need it. You're going straight in at IF, get digitized right away. So the IFs don't take the same path as the lower frequency or the microwave signals do, going through the receiver and the VNA. So there's just a basic interconnect. That's where all the cables are between the test set and the mainframe and the modules that you see in the system. That's what they do. Now, inside the module itself, there's a lot going on. And as I mentioned, we're not only up-converting or multiplying our source. You can see 2 bands of multiplication taking place. We're also passing through the signal from low frequencies up to 54 gigahertz. So we have a break frequency at 54. Then we go through the multipliers up to 80, 80 to 125, and then right out through the test port here. That's the 1 millimeter interface on the module. The signals coming back are going to go off this coupler here into these 2 receivers. So we have the reference receiver and the test receiver. And the IFs are then returned via the test set to the mainframe. So that millimeter extender consists of multipliers and receivers. So it's a full reflectometer. But it starts at 54 as far as the source, and it starts at 30 gigahertz as far as the receiver. Unlike more traditional broadband systems of the past, including the Anritsu previous generation, where you pretty much had your break frequency at 65 gigahertz, whether it be the source or the receiver. Here we're doing different frequencies. The reason is because the technology lends that to us. We're able to start these sampler-based receivers at a lower frequency, and we're able to also start our multipliers at a lower frequency. Because the sooner we move into the module, the better, because that helps reduce some of the other losses that we'd otherwise be facing. So things have changed over the years just to optimize the performance. Shifting to the 145 gigahertz module, the first thing you notice that instead of 2 multipliers, now there's a third one because we're going up to 145 gigahertz. The receiver can cover the full range up to 145 as well. Now the test port connector is a 0.8 millimeter as opposed to the 1 millimeter, but basically the same interconnects exist in this module. What happens when I go to 220? Anybody want to guess? I need one more multiplier, exactly. So I need to go one more stage of multiplication from 140 on up to 220. And my receiver needs to obviously cover the full range as well. And now what happened here, we no longer have a threaded coax, we have a 0.6 millimeter. And what I'm showing here is our probe connected directly to the module. But in terms of the interconnects, in terms of the functionality, they're all the same. It's just that one has more frequency reach than the other. Okay? But they're interchangeable. The fact is that if you have the baseband VNA, the test set, the only thing that changes is the modules, because the same interfaces are there regardless of the module and the band that it covers. Questions? Yes, yes.
Of the microwave thermal cascade that you have like SG or
Mm-hmm.
to load some after from the probe, do you have the same kind of model?
We do. When you're doing on-wafer measurements, it's a little different than when you're doing coax, because in the case of coax, you're loading a coax cal kit with all its parameters that comes with the cal kit usually. But in the case of the probe, you have to basically set up your own user-defined cal kit. And the VNA menu allows you to do that. You can import all the parameters for, say, the capacitance of the open, the inductance of the short, everything that's on that substrate. Because to define the cal kit for on-wafer, it's a combination of the probe and the substrate together. And you need to have those parameters from that vendor and introduce them into the VNA as a user-defined, or call it a custom cal kit. But once you enter those values once, you don't have to enter them again. Next time when you go to do your calibration, you define your test port to be the appropriate cal kit that you just set up, and go off and do your calibration measurements. Touch down on each standard, whatever order you like, open, short, load, then the through. Of course, you got to define the through too. Got to know what the length is of the delay so that you can put that in there. But the answer is yes, and that's one of the ways we have to adapt our VNA to be able to handle other interfaces. Coax is pretty simple. Waveguide can be pretty simple. But these other cases get quite complicated. And when they go to 4-port, and when they go from SOLT to LRM calibration, everything changes again. The parameters we enter will be very specific to the cal method we choose and the cal kit and probe we choose. So good question. I'll show some pictures of probe stations in a moment, but in the background on the menus, you would be challenged with entering those values. But as I say, the vendor provides that on a data sheet. They'll provide the capacitance of the open, the inductance of the short, the inductance of the termination. All those things are on the data sheet. And the length of the through, all those things are there. You just have to enter them in the right spots, and then it'll work. Yes. Is it time for a break? I think it is. All right, very good. We'll come back. This is a perfect place to break.
Yeah, just to let a message that because we will change something remotely as well. So a break for a coffee, and please join. Who is remotely? We will make some scheme here, technical scheme to put the slides for you guys.
So I'll go a little bit faster. But if there's any questions, please don't hesitate and ask, because I want to make sure that if I touch on some subject that's really of interest to you all, that we go, a little deeper on that one versus others. So do let me know. We just talked about the millimeter module that's used to reach 220 gigahertz and how that's unique. And you can see in this picture what I was referring to earlier. This looks like a waveguide interface, but it's not. It's actually a small, tiny hole in the face of the module with a small female center conductor or socket there. And that's 0.6 millimeter. And we use that as our coax interface, 0.6, to interface with a probe or an adapter. We make a whole series of adapters that have this same interface, 0.6 millimeter, that adapt to 1 millimeter or to waveguide like WR6 or WR5. But when we want to use this as a full single sweep system to 220 gigahertz, we really can't adapt it then. We have to use the 0.6 pin. And in this case, we partner with MPI, a company that makes probe stations out of Taiwan, with a lot of their engineering expertise in Germany. And this probe is what we use as our test port. This is what we will touch down on our wafer and provide the full band sweep all the way to 220 gigahertz. So this is a very unique interface, but it's the only way to do a coaxial single sweep system to 220 gigahertz. There's no other way. So it looks like a waveguide interface, standard UG387, with the alignment pins you see here, but it eliminates the need for the threaded connector, which we cannot make at these dimensions. Okay? That's the challenge behind this whole thing that had us working for years to develop this system, this interconnect system, to reach a single sweep 220 gigahertz system. Okay, it's not advancing. Did we lose the connection to the? Well, are we stuck? Oops. Back to the basics. Back to reading textbooks. That's better now. Let's see. Okay, I think it's working now. Yep, it's working. So just to summarize, the systems that we've talked about so far are broadband up to 110, 125, 145, and now 220. But as I mentioned earlier, the product line is very modular. So we start with a 2-port system, and then we can add some additional test sets to expand to 4 ports. So this can be accomplished with the same modules, the same mainframe baseband VNA. This one doesn't change. This test set here for a 2-port ends up at the bottom for a 4-port, and we add these 2 test sets to expand to 4 ports and additional two more modules. But again, it's a modular system, expandable as required. Now, the third configuration. So we've talked about the baseband or the module or the mainframe VNA, which is the unit at the top. We talked about a broadband system that uses a test set and a pair of extender modules. And now we're going to talk about a waveguide system that's based on either the VDI modules, Virginia diodes modules up to 1 terahertz. These are banded in waveguide. Or we take one of our millimeter modules that we use for the broadband system. This could be the 110. This happens to be an E band or a W band adapter. But in the case of the 220 module, if you think back to what I showed you earlier, we take an adapter and connect it to this 0.6 millimeter coaxial interface, and then create a banded waveguide system using the 220 module to go to WR5, WR6. Okay, so 110 to 170 or 140 to 220. When we get beyond 220, we've gone beyond the reach of our millimeter module, the single sweep module. So now we're entering into the VDI modules, which will carry us in bands up to 1 terahertz. But again, same baseband VNA is used. The VDI modules use an external power supply. The picture here is not totally up to date. The newer style of VDI modules are actually more compact. They're a little bit smaller than what you see here. And the power supply is also more like an AC adapter, like we use with the AutoCal or the OE module, smaller standard AC adapter rather than this specialized power supply. But again, it's an external power supply because these modules require a little bit more power than what we're able to deliver out of the standard test set here. But again, we can drive this with 70 gigahertz mainframe VNA or even lower frequency if all that's desired is a banded system. But if it's broadband, it's got to be one of these modules here to begin with. So how do we configure these? We start with the baseband VNA, we add the test set, and then the particular band of modules of interest. Down here, these are all the bands that are available from VDI. We don't need these lower ones typically because we can cover those with our millimeter module and just add an adapter as what we've done here with the Unicamp system, because the Unicamp system is effectively 7 systems in one. All right, and the way I get to 7 is by first counting the mainframe or the baseband VNA, then the 220 gigahertz system with the 2 modules, then the same 220 gigahertz system with a 1 millimeter coaxial adapter. So that makes 3 coaxial systems plus 4 waveguide systems. The 2 that we can create using the module and an adapter, and the other 2 that we create with additional VDI modules. So that's 7 systems built off the same mainframe VNA. And then we can expand to 4 ports. So now you see all of the different possibilities, starting with the mainframe VNA, adding the extra 2 ports for a 4 port up to 70 gigahertz. Over here is the millimeter wave broadband version, again using the same test sets but different configuration to get up to a 4 port 220 gigahertz. And we can do the same with the waveguide banded system with the VDI modules. It could be 2 or can be up to 4 as well. Okay. So you've got all this upgradability and modularity built into the system. But it all begins again with the baseband VNA and the fact that the VNA needs to be configured with the broadband interface. That's basically these 3 connectors across the top. That's a hardware option, but that's what provides the RF and the LO to the millimeter heads. So that's a hardware option that needs to be in place. But if it's in place, we can upgrade into the millimeter ranges. And we can also upgrade up to 4 ports by adding additional test sets or the waveguide modules for VDI. So one of our strongest benefits is the fact that it's modular. Everything's modular. All right. Let's talk about broadband and millimeter wave measurements and why they're so popular today and why are people looking for these higher and higher frequency VNAs. And in many cases, they need to be full band, full coverage, full sweep, single sweep, because we're doing things like device characterization that require a lot of data for the discrete device in order to build a good parametric model. So we'll talk about that. But these are just some of the different applications that are driving the need for higher and higher frequency design, characterization, all of the above. So we've got D-band, we've got E-band, we've got G-band, 5G, 6G, got other radar imaging applications. And when we're building devices for these systems, it's very important to not only understand how those devices perform in the range that they're intended to operate in, but also to understand what's happening with these devices at higher frequencies. What's the harmonic performance look like? All that gets placed into the device model to create accurate simulation. Not enough just to know what your device does in the band of interest. You need to go higher. So we have a broadband system to do that. So even if you're designing an amplifier to 40 gigahertz, chances are that the devices that go into that design were characterized to much higher frequencies in order to develop a good parametric model for that device. Because that parametric model is what gets used in a circuit simulator to design your amplifier. But you start with the very basic building block, which is a discrete device on a wafer. And we need to characterize that. And that's what device characterization is all about. And that is why we need these broadband systems, plain and simple. That's where the main popularity for these systems was started, was through this need for device characterization. So you kind of see how this moves up the chain here. We start with the basic measurements. Okay, we may do a whole bunch of these or only a few, depends on what the needs are. But device characterization refers to measuring many of these parameters. Most likely S parameters. That's going to be your most obvious thing. But if we're doing something that's nonlinear, we may care about IP3. We may have nonlinear VNA needs. We may have to do other noise measurements that are all related to developing a good parametric model. But most importantly, it's going to be frequency. We need wide frequency range to make sure that we get good S parameter measurements. Then we take all of this data and we begin to build device models. And a lot of the more popular software packages, IC-CAP is kind of the industry standard. A lot of device modelers use IC-CAP. They take data directly from the VNA, S parameter data, maybe some of these other things. And this software will generate the actual device model. And then that device model is then extended on up into the circuit simulation software that's available. So you see ADS here. Some of these are, from our competitors. We don't make software actually outside of the instruments. Only the software in the instruments. So these are dedicated software platforms for doing simulation. That's not something Anritsu does. But we need to be compatible in the models that we develop using the measurements that we perform so that we can have our users do their simulations in whatever platform they need to use. All right, so the VNA is used for the device characterization. We provide the data to the data modelers, the device modelers, so that simulation can be done properly. We care about this. This is the part we care about the most. This is device characterization. This is the actual measurements, and the VNA is the measurement engine to do many of these on this list. But we don't necessarily need everyone on this list. It depends, again, what the purpose of the device model is. If it's a passive model, well, then I wouldn't need nonlinear or IP3, just S parameters. So it really depends on what it is I'm trying to characterize and build the model accordingly. Now, this is what I used to work on some 20 years ago when the millimeter wave broadband systems were gigantic and the modules, the extender modules, were large and were very difficult to place on a probe station. So this is the challenge that we've addressed, the need that we've addressed to miniaturize and come up with higher performance extenders through all the technology developments that we've seen in the last 20 years. But when I first came to Anritsu, one of the early projects I worked on was this one, which was our first 110 gigahertz broadband system. And it was kind of ingenious that we put the modules at an angle like this, and got the test port as close as possible to the probe. But you can see there's still a fairly long cable there connecting to the probe. So these were really tough to work with because you had big modules, a lot of space between the module and the probe, and all of that contributes to drift and performance degradation. So flash forward 20 years, and now we have a module that's tiny, size of the palm of my hand. And if we mount it correctly on a probe station, we can eliminate the cable altogether. And that's really the biggest advantage here, is that you're delivering all of the performance of the VNA right to where you want it, which is at the probe, rather than have long cables and suffer a lot of insertion loss and reduced dynamic range. Plus, we're getting better raw directivity because we're bringing everything closer to the probe. A lot of these older systems, like these here, actually had negative directivity, which is a terrible thing because you had long cables back to the coupler, and so that created negative directivity, which if your raw directivity is bad, no matter how well you correct it, it's still going to drift over time and temperature. The idea is to get better raw directivity because that's what gives you the best stability over time and temperature, because you don't want to have to calibrate all day long. You want to make measurements, not spend all your time calibrating. But that's how it used to be in the past, is that calibrations would drift because of this reason. So we've addressed a lot of those challenges over the years at high frequencies. And you might ask, well, how do I mount these modules? Every implementation is going to be different. Every probe station manufacturer has a different microscope, for example, that they use. Every probe station manufacturer has a different size opening on their platinum where the wafer goes. So we have to adapt to those different mechanical configurations. Sometimes it's best to just have the module on a positioner, direct connected to the probe. Other times, in the differential case, we may need to have two modules side by side, because how else would you have a differential? Because this ends up being ground signal ground. This ends up being potentially ground signal ground signal ground. So you've got two signal pins here. So either you mount them stacked like this, or you mount them side by side. But on most positioners, if you're familiar with probe positioners, most of them at the end of their arms have these three holes. And those are the places where you place the probe generally. Well, what we've done with a lot of these bracket and holders is we've taken up that three-hole design. We place that whole bracket here, and then you can see the probe is in a different spot, offset from the module. All right, so a lot of this ends up being somewhat custom depending on which probe station you're going to use. This is a really good example of a system in France at SEAM, at Nanotech in Grenoble. They have a 4-port system, so you can see the ground signal, ground structure here. That's part of the cal substrate. That's the through here. And we're stacking the modules here. This is a 145 gigahertz system. So the two modules are stacked on both sides to create a differential configuration. And we're doing the calibration here. But notice how clean everything else is. There's like, compared to that other picture I showed you from 20 years ago, we've eliminated a lot of the extra hardware and created a much cleaner design on the probe station surface itself. And that's important because you may have DC probes and other things that you have to bring in. And so this just gives you a little bit more space to operate. This is a 220 gigahertz system. The one on the left is a 2-port. So there's the probes I showed you earlier from MPI connected to the 220 gigahertz module. This is similar to a system that we installed at Cornell University, a 2-port. They're about to expand that now to a 4-port. which would look like this, at least on one side. That's what it looks like. 2 modules. Instead of stacked vertically, they're stacked sort of horizontally, side by side, because we need to attach a differential probe to both modules, and that differential probe brings it all together at the substrate level to be a ground signal, ground signal, ground. So this by far is the most challenging setup I have worked on, up to 220 gigahertz on wafer, using a differential probe. These probes are typically, for these frequencies, the pitch between the ground signal ground is on the order of 50 to 75 to 100 microns. So they're pretty small. But again, we're still using a substrate that has all the standards on there. We probably don't use SOLT at these high frequencies because the standards just don't support that. So we're going to be using other methods like LRM, LRRM, or advanced LRM, where we use 2 reflex standards, we use a match, and we use a line. That's how we're able to do calibrations up to 220 gigahertz. But doing it in a differential world makes it even more challenging, on top of just doing it single-ended like this. I should mention the probes are field replaceable, but you don't want to break one. You don't want to be the guy that breaks the probe. They're very expensive, obviously. All right, so this is an installation in Germany at Ulm University, similar to the one I showed in the previous. This just gives you a better picture of what's going on. You've got 4 modules all on the probe station, 2 on the left and 2 on the right, to form your 2 differential pairs so that you can do differential S parameter measurements. And then the substrate down here, here are the differential probes. This is exactly like the system that I worked on 3 weeks ago at Cisco in New Jersey. They have a system like this. And again, working with the MPI probes and the substrate. This happens to be the through again, but you can see ground, signal, ground, signal, ground. That's the structure. So this is far more difficult than your coax or waveguide cals will ever be, because you are not only relying on all your connections and everything else being correct, but when you touch down on that wafer, it's all about the contact. And the planarity is really important. Planarity is just how well is the probe rotated reference to your substrate. So when you land the probe, you're landing all 5 contacts at the same time. You see these contact points here? These are the actual places that the probe is touching. So you don't want to be missing 2 down here, because then you obviously have a problem with planarity. Yeah, so that's where it becomes really challenging, is getting these mechanical systems set up perfectly so that when you touch down, you have the confidence that you're making contact properly on all of them. So this is really the most complex system that we can do today. It's a 4-port 220.
What kind of?
The probe or the substrate? The probe. The probe. Well, they used to be beryllium copper, but I'm not so sure. Today's are changing. Some are tungsten. There's other materials that are used for the probes. And then the substrates are ceramic substrates with gold. Yeah, they've etched all the standard. And then there's throughs. So typically on a substrate, you're going to get a whole line of standards. You're going to get a line of shorts. You're going to get a line of opens. And you're going to get a line of terminations, a whole row or column, however it's organized on the substrate itself. And then you're going to get a bunch of throughs as well. But on some of these differential substrates, it gets even more complicated than that. You have certain pairs that are terminated, and then the line next to it, and then the other line terminated. And so they vary depending on the frequency and the cal method, because you need certain standards for each cal method. Yes. Good question. So there are different probe stations out there. There are probe stations that are fully manual, which most of these are, because you want really to have all the control. And honestly, you don't want something to go on automated. And if you make one mistake, and that chuck, which has your substrate on it right there, that this section of the probe station down here is called the chuck. And if that level isn't set properly and you're running in an automated mode, why then the thing could come up and break your probe. So most of the people I know that are working in these frequency ranges with such expensive probes like this are not taking any chances with automation. There's really no need to, because this is more for device characterization. If I was testing wafers in manufacturing, I would want to have an automated system. But chances are it won't be as complicated as this anymore. It'll be just a standard probe, single-ended maybe. But in this case, you're doing device characterization. Almost everybody uses a manual probe station. The next step up is what's called a semi-automatic station. Semi-automatic station has the positioners that are manual, but the chuck movements, this part here, is moving under automated. And it knows the map of your substrate. And it also has the ability to follow your wafer around as well. That's called semi-automatic. And then there's fully automatic, where you've got a positioner that actually moves back and forth like this. Very rare that you would need that. Some LRM cases where the lines change, like in an LRL cal, maybe there's an arc. But again, most of the time I'm seeing manual stations, not semi-automatic or automatic. There's just too much going on. Yeah. And that's why you have the microscope here. And this is attached to a camera. There's a camera here, right? Right here, camera, microscope. And then there's a display somewhere behind there. I'm not showing in this picture. But this one had that picture. You see the display back there? So I'm able to see. Here's my microscope, camera, and I'm looking at this while I'm bringing the probe down one at a time. And if it's not going down right, I make an adjustment. Maybe the adjustment is on planarity. Usually it is for this. I mean, at 40 gigahertz, there may be some arguments to automating, because it just speeds things up. But you got to be concerned about the substrate surfaces too. They're not perfectly flat. So again, there's this concern that when the thing backs off and moves to the next standard, that it somehow hits the probe the wrong way, and you just can't afford to have that kind of accident. So I think the manual way to go is best. But yeah, for lower frequencies, I've heard of some automated cases as well. This was I can't remember exactly what the actual classification was, but you had to put on at least the lab coat and the on your shoes. Yeah. They are generally held in a clean room, but whether it's not always a class 100 or class 1000 is enough. Or yeah. I mean, I think it depends on the frequency, what you're doing as to what the clean room requirements are. The table, what you see here. So that's all part of the probe station. This section here, this is a large prober. This is like a 300 millimeter, I believe. But this surface here is what's called the platen. And it's part of the probe station. You can kind of see the Cascade logo right there, the form factor as they're referred to now. We're compatible with any of the probe stations out there, because a probe station is essentially a mechanical fixture, a very high precision mechanical fixture. But there's no reason why we can't adapt to any of the existing probe stations out there. The reason why we partner with MPI is because of the probe. MPI brings the only probe that we can use to 220 gigahertz in a single sweep. But this is just the surface here. So this probe station actually has legs and everything all built in to absorb the vibration and things like that. But the smaller probe stations, the manual ones, you'd want to put them on a certain vibe table so that they're properly isolated from any movements in the room. But this one is so large it goes to the floor, and it's all, you know, built in. All the shock absorption is built in. But that's a 300 millimeter prober. These others that I showed, this one here is smaller. So that's going to be on some kind of vibe table.
The table with the emitter array for DNA that you installed.
Yeah, the one you saw in Morgan Hill.
Yeah.
The one you saw in Morgan Hill is very similar to this picture here. One of them is like this. The other one is a 4-port, and both were manual systems. Both sat on a vibration table. So yeah, if you're ever in California or the Bay Area, please let me know, and I'd like to host you and give you a visit to our facility where we have everything set up. It's really quite impressive. We do a lot of measurements for our customers there too. We provide measurement services using these systems that we have in Morgan Hill. And Cynthia and Adriella have both been there and seen our setups. Next year will be the IMS show in San Francisco. Are you familiar with the International Microwave Symposium? It's held every year in some US city. Yeah, so next year it's going to be in San Francisco. So if any of you are presenting a paper there and want to come and visit, just let me know. The third week in June is usually when it is. Yeah. So San Francisco this year. And those of you who are going to go to the optical fiber conference in March for the electro-optical, that's also in San Francisco next year. So next year is the year for San Francisco. Both shows. Yeah. All right. So let's move on to another application. This is also on wafer. This is at Cornell University. They have a system like the one I showed earlier, this one here. 2-port at the moment, but they will expand to 4-port in the future. But they had an interesting requirement. The millimeter modules that we make, while they have excellent dynamic range, stability, and all these other great performance attributes, the one thing we don't have is higher power. Our power level is around -6, -8, depending on the frequency. Great for small signal characterization. But if you need to do high signal or nonlinear characterization, then you will need to use the VDI module as the stimulus for the device. So we can support, in addition to what I've shown you already in terms of configurations, we can support a hybrid configuration with one of the Anritsu modules here. This is the 220 module with the probe. And over here is the VDI module with a waveguide probe. Now, this is not a broadband system, but in many cases for these nonlinear measurements, they're not broadband. They're in a specific band, like D or G, something like that. So they can use our module as the receiver and then use the VDI module as the stimulus, because the VDI module puts out about 10 dB more. So if you're trying to do gain compression, some cases even more than that. If you're trying to do gain compression or IMD, then you need higher power to drive the device. Or if you're measuring power amplifiers, chances are the drive needs to be higher than what we're able to create out of these modules for small signal analysis. So that's where this kind of configuration comes into play, is for high power, nonlinear, on wafer measurements, driving say a power amplifier into compression so we can reach the power levels we need. So this is the Cornell, this is what we have set up at Cornell. Now Cisco wants to do the same thing, but do it differentially. We've already brought them the 220 gigahertz small signal system, but now we need to adapt that to do high power. So in that case, it's a 4-port. So we have to bring in 2 of these modules on the left side, and of course, our standard 2 on the right side. So the VDI modules can go up to around plus, well, it depends on the frequency. 10 is the maximum, yeah, plus 10. And ours are running at a -5. So you can see there's a difference. But for small signal characterization, that's good enough. But for these high power cases, they need more because they need to look at gain compression, for example. So you need to drive the device hotter to do that. No, the VDI modules does not have an attenuator. It's a fixed power coming out. Yeah. So you'd have to introduce an external attenuator to adjust that power. There's no electronic power control, and there's no attenuator, either a vane type or manual. No attenuator unless you insert it here between the module and the probe. But over here, of course, we do have the automatic level control that I talked about before. So when you're doing small signal measurements, you can handle the gain of the device by lowering the power electronically. So you have a little bit more flexibility with the Anritsu modules to do broadband characterization, but doing banded characterization, you can go to higher power. So that's the difference. These are the kinds of challenges we face when you're doing device characterization. No one system can do it all. Or I shouldn't say no one system. No one configuration can do it all. This system can do it all. All right, moving on to antenna measurements. This is another area of interest, especially at D band and G band and in antenna chamber applications. The millimeter modules by themselves lend themselves to a distributed VNA configuration, like I showed earlier with the low frequency VNA. Remember I showed a picture of a VNA that we said if I slice it down the middle, I can move the ports to where I want to go? Well, we're doing that already with the millimeter extenders. Everything is separated from the mainframe and the test set. All we need to do is extend the cables. We need to extend the cables so that we can create the measurement at the distance that we want to reach. So if we have the test set, the standard test set, the millimeter wave broadband test set, we can go to a 5-meter max on the source side, and we can go to a 10-meter max on the receive side. And in order to do that, we need a little bit more power out of the power supply, because obviously at those longer distances, we're going to run out of DC current and to reach the biasing that we need for the module. So one thing we've done is we've sort of beefed up the power supply that's in the test set to handle those longer cable lengths to reach the cables, or reach the modules. So it's similar in concept to what I showed you earlier, but that was at microwave frequencies. This is at millimeter wave frequencies. But the millimeter modules are already distributed just by design. That's how they are. We got a lot of people interested in on-chip antenna measurements. So this is combining on-wafer characterization or on-wafer calibration on one end, and potentially what I'll show you in the next slide will be how we receive the signal, and it's going to be through a horn antenna, because we're going to want to look at the antenna pattern. So we're going to do an antenna pattern measurement. But if you just want to measure return loss on the chip antenna, okay, we do that as a one-port probing measurement. So we're seeing this become more and more popular, especially as things are miniaturized further and further. Everything ends up on the same chip. Okay. That's what it extends to. So there's your on-chip antenna down here, and here's your horn antenna attached to one of the 220 gigahertz modules and on a robotic arm. So this robotic arm moves around in a systematic way to measure the pattern, the antenna pattern. So this was a very unique application for a 4-port 220, but it wasn't being used as a differential system necessarily, but they wanted 4 ports regardless. And one of the modules is sitting in this robotic arm with a WR, I think this was a WR6 horn attached to it. So again, it's the 220 gigahertz module with the 0.6 millimeter pin that we adapt to WR6, and then we attach the WR6 horn to that. And that's what you see here on this side. And down here, we got a module that's on the probe station doing this, okay, doing this contact onto the chip antenna. So
probe station in the left side?
There is a second probe station on the left side. So this installation at Penn State University involved a 4-port 220 system for 2 applications. One, differential measurements on wafer, which was on a separate probe station, and then antenna measurements on this probe station with the robotic arm. So there were actually 2 probe stations, 1 system, 4-port that was used here. I don't show the other probe station there, but it's right next to it. In fact, I think, yeah, it was on this side. It was on this side over here. So this here refers back to the block diagram I showed earlier of the millimeter module and the fact that the multipliers in the millimeter module start at 54. So everything up to 54 comes straight from this test port and goes into the module. But we're not running that long cable to this module. You can see the center conductor, I think, is not attached here. So we may only be using this portion of the sweep here. I think this was a banded measurement, so we didn't care about anything below 54. So we unhooked, and we knew that that cable was going to be longer because that cable had to come up the arm, you see it bundled back here, and then into the module. So even if I could put that cable there, there would be a lot of loss. So my measurements up to 54 gigahertz would be seriously degraded. And they're not necessary because I'm just doing, I believe was WR5 or 6. This was WR6. This was D-band. So the RF cable that we need to go to this module is running at 40 gigahertz. It gets multiplied up from 40 gigahertz. The LO feeds the receivers, the test and the reference inside the module. That LO is only 20 gigahertz. So I can support the 40 and the 20 gigahertz through this length. What I can't do is what's below 54 in the broadband sweep. That I leave behind. I don't need it because this is going to be a banded application. So we're able to do 54 to 220 by bringing a 40 gigahertz signal up and multiplying it to get here, and a 20 gigahertz to provide the LO to the receiver that's there. So it's quite a complex system. There's one that I was part of last year. No, earlier this year. It was in January. And I'm about to go back to Cornell to increase theirs from 2 ports to 4 ports. So that's another extension that's coming. Yep.
In this case, we don't have any phase problem.
I would say no, because the RF connection and the LO connection are less sensitive to movement. That's more safe because here we're multiplying up and we're using this as the LO for the receiver. It's going to be less sensitive to that because when I do the calibration, I'm going to calibrate that cable in. It's going to be part of the overall setup. It's whatever I attach from the interface where I do the calibration to where I connect to the device. That's the most sensitive cable. And I've eliminated the one that goes up to 54 gigahertz from here, so we're not using it. That would have been a sensitive one. That connection would have been sensitive to this kind of movement, because that's the connection coming directly from the VNA. It goes right through the module and ends up bringing the signal from 70 kilohertz to 54 gigahertz. But I'm not using that part. That part we're leaving alone. That would have been sensitive to the losses, the stability, and all that. But the LO and the RF are not. This gets multiplied up. It provides the LO for the receivers. If those cables move, there's not much change that takes place. Oh yeah. Oh, absolutely. All of this is still fully vector, everything. Yeah. But I thought your question was about calibration stability. And I think in the case of the RF and LO cables, I worry less about the impact of those cables on calibration stability. I worry more about the one that comes from the test port that goes all the way, but it doesn't in this case, since we're not using that portion. That's the one that I worry the most about.
Or you have another reference antenna.
You reference everything. So you basically, you take the two antennas, the one that's on the chip and the one on the robotic arm, and you look for the maximum point. You look for where the signal is maximum. So that means the antennas are pointed right at each other, right? So you adjust that until you get to that maximum. You set that as your reference. It's not the same as calibrations we do for other measurements. The antenna one is based on a maximum when you take the two antennas and point them at each other, and you get the maximum signal. If you want the proper gain of the antenna, then you need to do a power calibration followed by a receiver calibration. It's what I talked about earlier, because now instead of doing relative measurements, you would be wanting an absolute measurement. And for that, you need to have a calibrated receiver. And the only way you can calibrate a receiver is to have a calibrated source first and use that source to calibrate the receiver. Now you can measure the gain, but it needs an absolute measurement. All I'm suggesting is for the pattern, you just want the relative. You want it relative from the maximum. What does the pattern look like? There you just set the maximum to be 0 or whatever you want to call it, and then go from there. But if you want the absolute level, then you need to calibrate the receiver. Otherwise, I wouldn't worry about calibrating the receiver at all. There was a question in the back. Yep. Yeah. Going back to this one, absolutely. Yeah, yeah. You could have one as a reference, and the other, you could use a rotary joint. Yeah. 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 I mean, I think the thing to be careful of is what happens with the cables as you're turning things. You know, too much stress on the cable will cause performance degradation. So. Cynthia?
Question is only specialist to do another measurement. We need only the true calibration.
Yeah. Mm-hmm.
Continues the same thing.
Right. Yep. All you need is the transmission. You basically end up doing a transmission only, or what we call TFR, transmission response, CAL, TFR. Yeah, transmission frequency response. That's all it is. TFR. Yep. That's all we do. Unless you need the absolute value for the gain measurement. That's when things change. Then you need the receiver to measure absolute. All right. So I think that's the final example. Oops. I think I'm skipping here. So I'll just summarize on broadband. You've seen a lot of different applications. Obviously, the biggest benefit we have is the size of the modules. Allows us to adapt to a lot of different configurations on wafer antennas. We have the automatic level control for certain instances where you're measuring active devices. That's important. Not only to hit the high power, but also hit low power. So you can actually adjust the power level depending on what you're measuring. And the other important thing here is the frequency range. I mean, we're doing device characterization, so we want to go from the lowest frequency to the highest frequency. So we're able to do that with these broadband systems. Okay, so this is where I wanted to take the original break, believe it or not. But are there any other questions before we go on to the next section? How are we doing on time? Do we want to take a break now, or do we want to go another half an hour? Maybe we go another half an hour. Is that all right? Okay. Any questions on this section before I move on? This was really the biggest part that I wanted to cover, was introducing you to the system that's here at Unicamp, okay, and all the aspects of that system. Coax, broadband, waveguide, and then you could see some of the other applications that you could consider over time, like the on-wafer expansions to 4-port to do differential measurements. And now we're going to talk about an area that also is expansion of your current system, and that is optoelectronics. So there's no reason why, when we're characterizing electrical devices, that we can't also characterize the frequency response of electro-optical devices. As long as we can get back to electrical, the VNA is happy. So we need to be able to convert back to electrical so that we can do a standard calibration, and then we can de-embed or remove the part of the setup that we're not interested in. Usually it's the reference. We designate a reference and then we remove it from the combined measurement. So what's driving this? Obviously we have data center requirements, but we also have the long haul requirements that are driving data rates higher and higher, and therefore the bandwidths for the characterization of these devices pushes into the broadband range that I've already talked about. So instead of just using a 70 gigahertz VNA, now we're talking about using these broadband systems, because for the optoelectronic measurements, these are not banded. These are also broadband. So we have to have different wavelength capability. We have to have various bandwidth capabilities to get up to as high as 110. We are working on going higher than that because we have the electrical systems. So why not have the electro-optical part follow? Haven't quite gotten there yet. That's lagging the electrical part, but that is the future. So we're characterizing modulators, photoreceivers, entire transmitters, transceivers, anything that has an E to O or an O to E path, and everything that's electrical we can already do. So all the drivers that are used for the modulators, all the transimpedance amplifiers that are used with the receivers, we can cover all those things electrically. But this is adding on the E to O and O to E part of it. Where is this headed? Well, it's headed into what's called silicon photonics. That's what we're really seeing as sort of the future for a lot of this. The merging of the electrical measurements, the optical measurements, all on one chip. And going higher in frequency, which pretty much demands the broadband VNA that we just talked about. So all of these things kind of come together into one requirement as we head into the future with higher data rate needs. So this is just an example of some of the challenges that we face. We have to sometimes measure these devices where one side, either the optical or the electrical or both, is on chip. So we need to be able to probe, right? We have optical probes. We've worked with various probe manufacturers, MPI and others that have optical probes, but we also need to cover the electrical side like we talked about earlier. So now the challenge becomes, how do I calibrate? One side is probe, one side is coax. So again, the VNA needs to have the flexibilities to handle both interfaces. But this is what's driving things higher in frequency, up to 110, and in many cases beyond. What's the measurement that's of most concern here? It is the frequency response. It is the transmission response of the device. We want to know that the frequency response of our device can handle the data rates we intend to put through it, through that channel. So we need to make sure that the roll-off of our frequency response is adequate to cover the data rates, and the data rates are going to determine the bandwidth we need. So we have to measure what happens in the frequency domain through that electro-optical device in the transmission sense. Everything else we do is electrical. We look at return loss, that's still the same. That's on the electrical port. We're not looking at the optical return loss. This is the electrical return loss. We can do from the transmission, we can do group delay, and even optical insertion loss, we can characterize that using this approach. So this is what is driving the need for E to O and O to E measurements. But how are we going to accomplish that? We're going to start by taking our microwave VNA as is. We're not going to change anything. And we're going to connect an optical modulator. This may be what we want to test with the laser. And then we have a photodiode or photoreceiver to change that back to electrical. So we can calibrate our microwave VNA to the ends of those blue cables, just like we've been doing for any other microwave measurement. And then we can decide, well, which side do we want to measure, E to O or O to E? Well, if we're measuring E to O, we need a reference for the O to E that we can then remove from the combined measurement. Or we need our O to E to characterize a suitable optical transmitter and now use that to measure a photoreceiver, a photodiode. So it can go both directions. It depends on which is set as the transfer standard. The transfer standard is what we remove in the measurement. Right? But it all starts with the O to E module. And again, we want the transfer function. So this is our frequency response. We want to look at bandwidth, flatness, 3 dB point maybe. But a lot of these devices have a very gradual roll-off. So their usable bandwidth is far beyond, in many cases, far beyond their 3 dB point. So 3 dB point might not really be the right thing to look for, but is more, what is the usable bandwidth? If I'm down 10 dB and I can accommodate for that, why not? I can use it. And that's kind of how we operate in this electro-optical measurement. We're not so concerned like we are with other components about 3 dB points. We can talk about a usable bandwidth, but we need to characterize that. We need to know what that is. All right, so E to O could be modulators and transmitters. O to E could be photoreceivers or a path in an optical transceiver. And then we have even the ability to test fiber devices over frequency. Well, chances are a fiber device could be pretty flat, but there's some instances where an O to O device needs to be looked at for its frequency response. All right, so this is what a typical E to O measurement looks like. It's a 40 gigabit modulator in this case. So this is from a few years back. But when we look at the bandwidth, see, this is 10 dB down. And yeah, you can start to see a little bit of noise there, but it's still usable. In my opinion, it's still usable out to that 10 dB point. And I can still use it as a reference in this case. But I'm making that measurement based on my O to E module, which looks like this. So this is a project I worked on 20 years ago. And what came out of this was this OE module became the reference standard for everything we do in light wave component analysis. Rather than have a dedicated optical test set that has everything inside it and then have that interconnected to the mainframe VNA, we chose to keep things separate so that the mainframe VNA remains as a microwave VNA, and then we add the E to O and O to E as needed. So we can change wavelengths and we change bandwidths. So it makes it a much more flexible measurement solution for this application. But what's unique about this module is that it's got the photodiode on a temperature oven, kind of a temperature stabilization. And then over here on the right side is the voltage regulator that keeps the bias regulation. So we have bias regulation, temperature stability, very important. And we have everything packaged inside so that... You have a question? Yeah. Okay. You want to ask?
Exactly the reference of this.
Mm-hmm.
Perhaps you will make.
Oh yeah, no, I'm going to make a comment about that. Yeah. So we got all the fiber and everything internal to the module, so you don't worry about any kind of damage, static damage otherwise, to the photodiode. But what is really one of the most important aspects of this is the accuracy of its characterization. That characterization of magnitude and phase to, in some cases, 70 gigahertz and others up to 110 is based on a national standard that we get from NIST. So that's the US National Standards Lab. We send them a photodiode and they characterize it. And I'll mention in a moment how they do that. But once we have that characterization, we can then use our VNA method to characterize these modules. So we're transferring effectively a characterization that was derived from national standards onto the actual OE modules that we provide. And that's really important. That's how you get the accuracy. It all starts with this module, and then it can be transferred to the optical transmitter after that. So it works in both directions. So that's what gives us the improved uncertainties. The other thing that's interesting here is that if you've ever worked with photodiodes, I'm sure you know that if you apply an optical signal without a bias, you can damage a photodiode very easily. So we built into this module a battery backup, which protects the photodiode in the event that somehow the AC adapter is removed. So this is where the AC adapter goes right here. If that gets removed, then the battery kicks in and keeps the photodiode biased if your optical signal is being applied, because that can pop the photodiode otherwise. So so these are very robust. In 20 years, I've never seen one of these fail. They take a lot of handling, but they've never had problems because of all the, backup and other things built into them. The E to O converter we get from a third party. You all know Thor Labs. They build this to our spec so that we can use this in our optoelectronic VNA. It has an integrated laser modulator and a bias controller. So the idea here is that we get a constant modulated output at this port here, coming out of the, actually it's this port here, coming out of the E to O converter. So there's a closed loop bias controller, internal laser. So it's a complete optical transmitter in one box. And in the application, we put the two together, and now we have an E to O and an O to E. And depending on what we measure, we substitute one for the other. So if we're measuring an E to O device, obviously this wouldn't be here. We use the O to E module, measure whatever is here, de-embed this, and we have a measurement of the modulator. If, however, we want to measure an O to E device, then we need the characterized E to O converter. And we get that characterization by using the OE module to characterize, and then we can de-embed the O to E or the E to O when we're measuring a photodiode. So either way, we're just doing a simple de-embedding. But again, we need to know what the file is. So we need that characterization. And it has to be derived from national standards to be of any use. So this could be a 40, 70, 110 gigahertz VNA. So it could be the broadband one. I only show the baseband here, but it could be the broadband. And we have a variety of different wavelengths and bandwidths that we accommodate.
By yourself with you, or you have like a file that describes the.
So when you get the ODE module, you get the characterization. It comes from our calibration lab. That's how we provide it, because everything you do in this application starts from here. Yes. Yes. Correct. Correct. And then once you have the E to O characterized, then you can use it to measure something else over here. Yeah, it's a two-step process in that case. If you yes, magnitude and phase. And I'll tell you how you get that in a moment. That's the next slide. That talks about how we get the derivation from national standards.
Apart from your question, you can create your reference as well device, but it will not change with all the characterization and all
Yeah.
the stability that it requires you. So you can build your golden sample.
Yeah, I mean, I've had people use photodiodes from various vendors, and they don't have the same temperature compensation, bias regulation. They're not as robust. In other words, they're discrete diodes. And then the vendor gives you the S2P file. Well, how did he get the file? How did they get the file? How was that derived from national standards? So I strongly recommend for the EDO and ODE measurements to at least have the OE module, because that's the reference. If you need the EDO converter, we have that too. But I have plenty of people that will have their own modulator that they'll use here. But modulators drift much more than a ODE will. So it's very important to have that ODE be rock solid and accurate in terms of its characterization. So then you can use it to characterize a modulator that may be drifting a little bit. This one doesn't because it's got the bias controller built in. But a discrete modulator left on the table, on the bench, can drift. But generally what drifts on a modulator is the absolute level, not the shape of the response. The absolute level will go up and down, but the shape generally stays the same. But it's still annoying to have that level going up and down. It doesn't make you very confident about the measurements you're making. So again, the OE is critical because that's what sets the derivation from national standards. That's what sets the accuracy and uncertainty of the measurement. And then the EDO is nice to have because it's very stable and can be characterized based on the ODE. So the two do go together. But if all you ever test is modulators, well, then you, of course, you don't need the EDO because you have your device will always be here. But if you're doing photo receivers or photodiodes, you're going to need to have a stable optical transmitter that you can characterize based on this standard there, that ODE module. So that's how it works.
If you go up to 110 gigahertz,
Mhm.
you need 2 EO to have it on 5 and 90 nanometers.
So for the ODE,
110
we have,
for the EO.
yeah, for the EO,
I need 2 models in this.
for 110, we cannot make one optical transmitter for 2 wavelengths up to 110. It can't be done in one. The one modulator won't support both wavelengths to 110. We can have a modulator that supports both wavelengths to 70 gigahertz, but not to 110. But on the OE side, you can see there's a combo both at 70 and there's a combo also at combination also at 110. Yeah. But yeah, up to 110 on a modulator, it's very difficult. Yeah. What we've found over the years is the modulator will always lag behind the photodiode. The photodiode will be higher in bandwidth long before the modulator will. So we're kind of playing catch up here with the modulator versus the photodiode. So, but what's important for us is that photodiode be stable and that it is the way it's designed here with the bias control, bias regulation, and the temperature compensation. That's the most important thing. Any other questions on this one before I move on? Because this is what's going to explain to you how we get the derivation, because the derivation comes from national standards, in this case NIST in Colorado, but they're using a different method to characterize the so-called golden reference. The golden reference is the photodiode that we retain in our Cal lab. It doesn't ever exit the Cal lab. It's always in the Cal lab. And it's used to characterize the modules that we provide our customers. So it starts with an EO sampling technique, which NIST does, where they're applying a very fast optical pulse to the photodiode, the golden standard that we send them. They apply a very fast optical pulse, and then they take the response out of that and do an FFT. And they give us magnitude and phase. That's how we get the magnitude and phase. Otherwise, it would be impossible. It comes from this method, EO sampling. And this is a well-published method. NIST has written, there's many articles out there, and we've been using this for 20 years, at least on the lower frequency photodiodes. And then we take this golden standard, once it's in our Cal lab, and we use the method that I've already showed you for the VNA method to characterize the OEs that we supply our customers. We have obviously a optical transmitter in our Cal lab to do this, because we have to go back to this again, put our primary golden diode here, our golden reference, use that to characterize our optical transmitter. And once the optical transmitter is characterized, we can go off and characterize these OE modules all day long. But it has to be set by the golden standard, which is this one. It has to start there. And the fact that it's getting characterized at NIST using a different method is what gives this a lot of credence, you know, and much more confidence, because it is derived from national standards. Okay. All right, that's, whoops, this keeps jumping ahead, sorry. That's it on the optoelectronic. I've introduced to you the method that we're using, up to 70 gigahertz, 110, multiple wavelengths. We not only offer the EDO and ODE by themselves, we offer the whole entire system with a VNA, and we call that the optical electronic VNA. And then we have the internal VNA calibration software, which is basically de-embedding, because we're going to take our standard microwave calibration and we're going to de-embed either the photodiode or the optical transmitter to focus on the measurement we want to make. And that's all done using the de-embedding menu, which we just take a subset of that and make it an optical optoelectronic application. We don't have to do all the de-embedding that we would normally do in an electrical case, because we don't really care about the reflection part. We care about the transmission when we're doing these measurements. So we came up with a simplified de-embedding just for this application. It's separated that out in our user menus. Everything else I've talked about. Stability and the national standards derivation, probably the most important thing. So this is a good place to take a break. Yeah, next topic is signal integrity. So normally I do things in the opposite order. I do the electrical first, then the optical, but I know that this group was more interested in the optical side, so I jumped right to that. Now we're going to talk about the electrical part behind that. As we're going to higher data rates, there's other measurements that are important. So we'll take a 15-minute break. Okay. Yep.
We are back from the coffee break now with the last section about signal integrity. We should spend more 30 minutes on this section, and later on we go to the lab. We invite you guys to meet in person up to 500 gigahertz. And I open as well. I know a lot of curiosity and lots to learn as well. I let it open our email and our contacts. Anything that you want to go deeper, please feel free to ask us. We can schedule a meeting or a section to any other subjects related to that. So feel free to ask us later. Thank you.
Thanks, Adriela. So yeah, I'm going to keep this last session to around 30 minutes, and then we'll take a tour of the lab, because we really wanted to do that as well. So I'm going to postpone the active measurements for a future session, all right? Next year, when we'll have a user group and we'll have some discussions on actual measurements, and there'll be more questions. So I invite you to do that. Use the equipment here and give us the feedback, because that'll be the basis for a user group and another session in the future. We'll go into more depth on wafer measurements. I have a whole seminar on just on wafer measurements and what's needed to to set up the cal kits and actually what calibration types to use. We haven't discussed any of that today, so we still have plenty more to cover in a future session. So this last part is about signal integrity, which really refers to high-speed electrical interfaces. Yeah, thank you. Would be good. So my voice is kind of drying up here as we go. And so what are we looking at? We're studying the electrical quality, call it the quality of the electrical signal. Okay, and how is that electrical signal being disturbed? Okay, how is it being distorted? Let's say, is through the channels that we're putting the signals across, and obviously the channels that we're designing, whether it be on a backplane or in a cable assembly, they need to be able to handle the data rates that we intend to put through them. Just like we were concerned in the E to O, O to E case, here we're just talking about pure electrical. But again, it's important to have these channels characterized fully so we know what they're capable of doing. And in some cases, we may be able to apply some pre-emphasis on the signal to sort of balance out some of these cases, and we can actually improve the signal quality as a result. By knowing what our channel is doing, we can correct for it on the signal side. So that's why some of these channel characterizations mean a lot to the signal integrity engineer. So as we all know, VNAs make measurements in frequency domain. That's what a VNA is all about. We're doing swept CW signals, applying stimulus, measuring responses, reflected responses, transmitted responses. But we also use instruments in the time domain, scopes, TDRs, BERTs, and Anritsu makes some of these instruments too out of our Japanese division. So the intent here is to augment the information we're getting from time domain instruments by adding the frequency domain as well. So we're not trying to replace a frequency domain instrument. We're just trying to get some extra insight out of or replace the time domain instrument by getting some extra insight out of frequency domain instruments to augment the knowledge we're getting about our channel. So TDRs, most of us are familiar, are time domain instruments. They apply a very fast pulse, and then there's a signal reflected back, and they're good for measuring where there's discontinuities on a line. We can essentially set up the same kind of measurement from the frequency domain by doing an inverse FFT. And so we're going to use time domain to sort of emulate the same capability, but from the frequency domain side. The problem with the time domain instruments is they're a bit limited in dynamic range. So we intend to overcome that by using our VNA that has a lot more dynamic range and a lower noise floor. So how do we do that? How do we get a lower noise floor? We get a lower noise floor through the VNA receiver, which is inherently narrow band, where the scope or the TDR is wideband. The VNA is a narrow band instrument, so we can control our noise floor and our dynamic range and get better accuracy. So we're going to characterize these channels and get the S parameters, S2P, S4P. Most of these are going to be differential measurements, so we're mostly looking for S4P data. And then we're going to use the time domain, which is the inverse FFT, to look at this frequency domain data in a different way from the time domain side. And what we're looking for is the discontinuities, things that influence the impedance of the line, that make it not perfect. We want to find those discontinuities and, fix them if we can. So what we're seeing, of course, in the high-speed digital world is higher and higher data rates, and they're continuing to increase. And a lot of these characterizations, as we talked about earlier, for device characterization, we need not only the device data up to where we want to use it, but we need it beyond that to get accurate models. So here again, we'd like to get beyond, well, at least second, third harmonic would be nice to have. But that pushes these bandwidths to beyond 70 gigahertz really easily. If you start with a 28 gigabit system, well, ideally we want to test out to 70 gigahertz. So quickly there becomes an argument for much higher frequency VNA to really get the best characterization of these channels. So we need a 4-port system because most of these interconnects are differential, balanced differential. So we have the 70 gigahertz version here with the mainframe VNA 2-port with the test set to expand the 2 ports to 4 ports. We take those 2 units here, put them at the top of this stack, and add 2 of the millimeter sets that you've already seen to expand to a 4-port broadband system up to 125, 145, or even as high as I showed earlier in the 220 case at some of the universities that I've worked with. So let's get to the basics of time domain. Let's say I have a passive device, as simple as this connectorized transmission line. If I look at things in frequency domain and I happen to have a problem on that line, I'm just going to get a poor return loss, and it will look poor across the frequency. It won't be able to really pinpoint where the problem resides. Where in the line is the discontinuity that's causing the poor return loss and therefore bad transmission characteristics in my channel? This is a very simple application, but imagine a longer line where it's even more difficult to try to figure out where the problem lies. If you're just looking at the data in frequency domain. So ideally, so this is what it looks like in frequency domain. Okay, I've got a bad return loss, obviously, but where's the problem? Well, this is where we go into time domain. And most importantly, we go into low pass time domain, where we can use something called step response, which emulates the way a TDR trace looks, where we can actually see what's happening to the impedance. Not this one here, but the next one I'm going to show you where the impedance is as a function of distance and time. So that's where time domain really helps, is in a troubleshooting way. When you're looking at some data for a channel and it doesn't look right, some loss, poor return loss, how do you find out where that issue is? Well, time domain allows us to resolve things, and depending on how much frequency range you have in your VNA, the resolution improves. So if you get up to these higher frequency, higher bandwidth VNAs, why, you can see we get down to like millimeters of resolution. So we can accurately pinpoint where these problems reside. So the bandwidth of the VNA is basically inversely related, or the resolution is inversely related to the bandwidth of the VNA. So the more bandwidth, the better the resolution. So the TDR display is a step response on a low pass time domain. And what we're able to profile is the actual impedance of the line as a function of distance or time. This is what we call a Beatty standard. This is a handy device to use to sort of demonstrate the capabilities of the step response low pass time domain. We can profile the impedance. So this would be under normal conditions, this would be the 50 ohms here. And then there's a section where it transforms to 25, and we can pick that out in the TDR display, and then it goes back to 50 ohms. So this kind of information that's available in time domain that you wouldn't see out of the frequency domain side. But I have to say, time domain is still one of those things that's not as well understood by most VNA users. But the power of it is actually quite impressive, what you can get in terms of troubleshooting capability. So TDR is something that your signal integrity engineers want to see. That's what they live for, is that. The other thing is eye diagrams. And we can also simulate an eye diagram by using frequency domain data and a mathematically generated data pattern. We don't have a pulse pattern generator in the VNA like a BERT. We don't have a PPG, so we don't generate our own data pattern, but we can mathematically simulate one and do a convolution, mathematical convolution with the actual frequency domain data that we're measuring and simulate the eye diagram as a result. So we can do PAM4, NRZ. So this becomes an additional function in the time domain suite for simulating the eye diagram. Now, it's not going to be as fast as a scope, but it should be very representative of what you see on the scope. Very similar. But it's got all the frequency characteristics and the error correction applied to it. So, so again, another way of seeing something that you're familiar with, but seeing it from the frequency domain side. This is how we set up the eye diagram. It's pretty straightforward. We pick the data stream, so the signaling format. We pick the pattern length, so we can support a number of different pattern lengths. Data rate goes here. And of course, if I don't put any real rise and fall time in there, it's going to be perfect because this is mathematically generated. So, but I can put in some rise and fall time. And then we can add jitter and noise as well. So we can make it look very real world. And then we can adjust the data rate and see what happens. Very important in all this, whether you're looking at TDR or eye diagram simulations, is having reliable low frequency data. The lower you can go, the better. We talked about this earlier, Bruno and I did, about the fact that if you're doing time domain, you have to extrapolate down to DC. That's part of the inverse FFT. So you have to do this extrapolation. If you don't have low frequency data points, you're going to get a little bit more error as you extrapolate down to low frequencies, because we don't have the low frequencies inherently measured here. We have to extrapolate them. Scope gives you the whole range, right? So this is where the low frequency data that we measure comes in. It's very important, because the more low frequency data we get, the more accurate the eye diagram simulation, or the more accurate the time domain, the TDR. Because if the TDR that I showed you earlier, if I don't have the low frequency data, instead of seeing this flat section, you probably see something that has a little bit of a ramp in it. So it would not be as accurate, again, because of the low frequency data. So the importance of low frequency data just can't be understated here. It's crucial for getting accuracies in time domain. Here's an example to 110 gigahertz. This is a PC board that has a differential trace on it. This is the one I'm connected to in this particular example. And instead of just measuring single-ended S parameters, this is a 4-port, so we're using the VNA to measure actual differential S parameters. So differential S parameters are computed from single-ended S parameters through mathematical superposition. And we're able to take S11 through S44 and transform that into the differential return loss, input and output. That's what you see here on the top. This is the return loss. Next one is the transmission, forward and reverse. But these are all differential. So you can see that the nomenclature here changes as a result. This is D2, D1, which means differential in the forward direction. And then down here is the TDR. So what can I see in this TDR? I can see that the impedance is 100 ohms, which is what I would expect, because it's differential. And I see a little blip here. That's the connector, because I've started my reference plane at something a little ahead of 0. And I see the connector where I'm actually touching down on the board. And then I'm profiling the impedance of the line throughout. And then on the far end, there's another little bit of a peak there, and that's the connector on the opposite side. And then there's the eye diagram. So all of these measurements can be made simultaneously with one sweep. And all of them get updated with every sweep that follows. So this is a live measurement. It's not one where you take the S4P data and put it in a simulator. You can do that too. Many of you may know about PLTS. That's a software from Keysight that takes the S4P file and cranks out the eye diagram. But this is actually happening live on the. It's just another trace. It's just another measurement that you can set up on the screen, and it's getting updated with every sweep. Another topic in signal integrity that comes up often is network extraction, which then leads to de-embedding. So there will be occasions where the device you want to measure is inside a board, and you can't calibrate on those inner levels here. You have to calibrate back at the connector. And how do you do that? So that you can remove those launches and just measure the device by itself. So you need to extract these lines somehow. And that's what's known as de-embedding. De-embedding is the ability to add and subtract S2P or S4P, in this case S4P, from your measurement. Because ideally you want your reference plane to be here, not back here. But the calibration I do has to be done here because I have no way to really calibrate. I don't have any way to bring open short load inside the fixture. So unless I had a probe. I mean, if I had a probe, I could maybe do a probing measurement on a PC board. That might be one way to do it without the device present. But more commonly, we would use something called network extraction, where we actually measure just an open at that reference plane inside. We don't need the short and the termination. We just measure an open. And that allows us at a first level to get two calibrations, one at the coax, which will be a full one-port cal, all three reference standards. And then at the inner reference plane, I'm just going to measure an open. And that's enough information for this universal fixture extraction algorithm to give us the characterization file for that launch. That's what we want. We want that S4P file. So this is a way of getting an S4P file for de-embedding, but getting it with less calibration standards on the inner plane being right here where the device would go. I think Keysight calls this automatic fixture removal, if you're familiar with that. AFR is what they call it. We call it UFX. Slightly different algorithms, but they kind of do the same thing. They get us the S4P file, and then once we've got that, these are the tools that are actually used to get the S4P file. And again, for the 4-port case, what we want to do is break this into two pieces. And so by measuring certain standards, we're able to extract these S4P files effectively. And then once we've got the file, we go into our embedding, de-embedding menu, and we apply to the correct port, we apply to the correct port what it is we want to de-embed. We load the file, and then we drop it down in there and apply it. And now we've moved our reference plane to where the device is that we want to measure. But as I said before, network extraction is what's required to get us to this point. We can't do the de-embedding until we have the actual file, and then we can de-embed it. So that's how de-embedding works. It relies on that S4P file. that you get through network extraction. Have any of you done this before? No? Okay. So,
Is it possible to do de-embedded? I think it's possible, but I'm not sure. With antennas, when we measure input impedance of antennas, we can pull out, we can have an antenna, a microstrip antenna and a lead line, and then you have a connector. I think it's possible to de-embed this connector and to measure only
the antenna by itself.
line and patch. Is it
Right.
possible?
It would be if you have a characterization file for the connector. So
Excuse me?
you need a characterization file for the connector because you're going to do the calibration at the end of your cable.
Yeah.
Then you have the connector that's on your antenna, right? But you don't want the connector to be part of your measurement. So
Can I use
this is a perfect candidate for de-embedding. This is a perfect candidate, but you need to have the S2P file. So you need to get the S2P file. So you have to use, right. So you have to do that using network extraction.
But she can measure it.
You leave it open.
No,
That's
one
it.
side you don't-
One side is open.
One side is, I don't know.
Well, it's threaded. One side is threaded.
The other side sometimes is a launch.
Right.
And you don't have how to.
But can you remove, can you take a connector just like the one that's on the antenna with nothing attached to it? Can you get a connector similar to the one that's on the antenna? Just the bare connector. Then you can do network extraction.
Yeah, I can do-
You start with a one port on this side.
Then I needed a fixture extension.
Yes. But yours is going to be simpler because it's only a 2-port. What I was talking about earlier for signal integrity is all 4-port because it's all differential. And differential stuff is far more difficult. Believe me, it is. But in your case, you would be using what's called type B. This is called type B network extraction. And for that, all I need is a 1-port calibration at the end of the cable, open short load, save that, get your connector, just the connector by itself, add it onto the cable, and measure it when it's open using type B network extraction. Now, once that measurement is done, that open is measured, you will get an S2P file. And now when you make the measurement on the antenna, you can go to de-embedding this menu, and you've done your calibration to the end of the cable, right? Attach the antenna and take your S2P file that you got from the previous step, apply it to port 1, load it, and drop it down in here and turn it on. And now you will effectively remove the contribution of the connector from your antenna measurement. What you're left with now is just the trace and your feed or whatever, or the antenna, right?
Much more interesting to compare simulations.
Yeah.
Really know that the simulated antenna is going the same direction to the experimental.
And that has to be done without the connector. So you can match the simulation.
Yes,
Simulation doesn't have the connector, right? No.
sometimes you can
The other way you could do it, if all you're interested in, and in this case, all we really care about is return loss. How many of you know about gating in time domain? How many have heard of that? We didn't even talk about that today. But if you're in time domain and you see those discontinuities that we were looking at earlier, you can put a gate around the discontinuity, which in most cases is the connector. So first you look at time domain and you see your connector is there. Then you put a box around it and you cut it off. And now you go back to frequency domain. And what you're going to see is the frequency domain behavior without the connector. So you have another way to do it using gating in time domain. Right? So you have de-embedding and you have gating in time domain. Both work. I mean, provided you're not doing transmission, this is going to work for reflection. Yes. Sure. Yeah. And that is probably the easiest way to do it. And maybe the most accurate, because if you're doing network extraction and you're only going to use the open, you're going to get some ripple actually in your response. So the best way, I think, is going to be gating in time. Set up your time domain, find your connector, gate it out, and go back to frequency domain. And there's your measurement. All right. Questions? That's it. So this is just a summary. All right, low frequency. I can't overemphasize emphasize how important low frequency data is. And so that's something that this VNA is capable of providing because it's got the RF and the microwave ranges. And we talked about network extraction. We talked about TDR, eye diagrams. The one thing we didn't talk about is true mode, which is used in non-linear differential measurement. Because the assumption that we've made so far when we calculate differential S parameters is that everything is passive or linear. So the mathematics works out correctly when I convert single-ended S parameters into differential. Where that breaks down is if the device is nonlinear. And that's when you get into this whole topic of true mode, which requires two sources, not one, because you can no longer just switch the source and then gather all those measurements and use mathematics to compute differential quantities. But in this case, you need to actually drive the device with a true differential stimulus, which means two sources 180 degrees out of phase of each other. We didn't talk about that today because the VNA that we have here at Unicamp is not set up for that kind of nonlinear. We have not talked about any of the nonlinear measurements at all, or the active stuff. We're pretty much concentrating on passive measurements for the most part. So that's all I have. Well, actually not true. There's more, but we're not going to cover the rest. And maybe in a future session, we'll go into more depth on whatever topics you're interested in. Just let us know. I mean, this is where we want your feedback to give us some more ideas, and we'll entertain them.
What's fun about it, we're talking about the measurement, 200 gigahertz and everything, but you decide that it's more important to working on 7 kilohertz.
Well, actually, both are important here because at the same time, for the TDR, you want resolution. And what does resolution mean? Higher frequency. So both are important.
Something like if you start at 10 megahertz,
yeah,
doesn't seem too
far away
from 70.
But in the case of that DC extraction that we talked about, extrapolation. Yeah, I mean, here the 70 kilohertz is referring to what we need to do in time domain extraction, right? We can't get there otherwise. So we need the low frequency. But yeah, of course, the high frequency, that's the main message of the day. has been the 220 single sweep. Yeah. All right. Well, thank you all for attending. We invite you now over to the lab so we can show you some of the actual equipment we have set up right now for the 220 to 330 system. Those are the modules we have currently hooked up to the VNA. But we have all the other ones out just to show you the 7 systems in one that I've been talking about here. So thank you all.
People that is online, thank you very much. Now we go by presence. So the invitation is open for you one day that you came to Campinas visit us. Bye-bye.